Today marks the grand finale of our ATAL Faculty Development Program. Over the past few days, we have been on a journey of learning, discovery, and inspiration. Today, we reach the concluding chapters of this journey. But as every ending is a new beginning, let us treat this as a launchpad for our future academic explorations. We have three enriching sessions lined up till 6:30 p.m., after which you will be submitting your feedback and taking the online test. So let us dive into the proceedings with enthusiasm and focus. To set the tone for the afternoon, our first session will be led by Mr. Nimit Gandhi, sir, whose insights promise to broaden our perspectives. Mr. Nimit Gandhi is a highly skilled FPGA IP design engineer with over 7 years of expertise in RTL design, FPGA architecture, and high speed protocol development. He currently serves as a staff engineer at Lattice Semiconductor, Malaysia, driving FPGA IP development for video applications. Earlier at Intel Microelectronics, he contributed to 5G mobile communication, IP design, and execution. His technical strengths include RTL architecture, synthesis, timing analysis, and verification, with hands on experience in tools like Vivado, Quartus, and Model Sim. He also pursued research as a JRF at the MS University of Baroda on flexible solar cells supported by DST and earned a gold medal in MSc Electronics from Sardar Patel University. Beyond engineering, he is passionate about teaching, music, environmental sustainability, and knowledge sharing. Dear participants, let us extend a warm welcome to our distinguished speaker. Sir, over to you, sir.
Thank you, Dr. Shruti, for the introduction. Yeah. Okay, shall we start?
Yes, sir.
Okay, let me share my screen. Let me know once you can see my screen. Hello.
Sir,
Yes,
it
sir.
is
Screen
visible.
is visible.
Yes.
Okay. Okay, so let's get started. So I think already you, first of all, I would like to thank the, I think, can you please the mic on mute? There's some noise.
Dear participants, please switch off your mics. Dear participants, please switch off your mics.
Okay, now it's good. Okay, so today I'm going to talk about the low power VLSI design for the edge AI computing. Okay, but before moving to that, I would like to thank for this opportunity to share my knowledge and my experience, the industry experience to share with the faculty members. So actually, I'm very happy to contributing for this program because the faculty should be aware with the current industry trend, right, and the technologies, and so with that knowledge, whatever I said today, that the faculty can use and blend it with the theory part and the practical part and to serve the student. So student also will be aware with the industry trend before they go to the actual industry. So I'm glad to be here and share my knowledge and the experience. Okay, so I think pretty much introduction is already covered by Dr. Shruti. So, but this is the roles. And so I actually did my bachelor with the BSc instrumentation. So right now the all faculty members are engineering, right? So I actually still regretting till day that because of my poor merits, I was not able to get the seat into the engineering. Yeah, but uh, doesn't matter whether you learn electronics from engineering or the science. The electronics is electronics, right? So I did my bachelor with the BSc instrumentation, and then I switched to the MSc electronic science because I wanted to learn the wide all the subjects of the electronics, not just focusing on the automation and control parts. So that's how I decided to uh, go to the master program for the electronic science. And after my master, I started my career with as a service engineer for the high power UPS system that is used by the oil and gas and oil, gas, and the chemical industry, or any processing manufacturing industry which uses the automation, the DCS and SCADA system. So this UPS used for that system. After that, I also got the GRF opportunity to work as a GRF for the flexible solar cell. So I worked on the sputtering method and physical vapor deposition to grow the solar cell on the flexible substrate. So you can twist the solar cell, roll it over. Okay, so that kind of application. So basically, I started my career in the VLSI from the system level solution as a junior FPGA engineer, where I worked for the USB protocol. Then later on, I moved to Intel Malaysia, where I worked for the 5G, and currently I'm working on the video IPs for in the latest semiconductor. After after that, the roles I played so far, right? But I can think of myself as a curious mind. The curious word is actually small, but it's enough to ignite the ideas, and it's help us to solve the problems, critical problems. It help us to do the critical thinking. Yeah. So why I say myself a curious mind? Because whenever I see something, some machine, some electronics, some products, every time my mind tries to think that, okay, what exactly the principle used inside that, how they made it, what is the thought process to make that product, right? So that thing, that curious mind, we should have at every stage of life. So that is the that's my story. Okay. uh, and then the next is what brings me here today. So in 2 words, I love teaching because that I enjoy the most whenever I teach someone, because the teaching is the process in which I also learn, and the other person also getting something from me. Okay, so that's all about my story. So what's ahead for us today? So basically, these are the topics I am going to cover. Okay, so it's basically about the edge computing, then the different types of architecture used in the cloud architecture, the network architecture, and then what are the VLSI design consideration for the edge AI designs or edge AI products. So these are the topics which I'm going to cover it. Okay, so presenters note. So be curious, because this isn't a AI generated. It's a crafted with passion. Stay present. You will enjoy the journey because nowadays too many things done by AI, but this is not.
S- Hello, sir. I
Yeah,
think slides are not moving, sir.
is it? Uh, Wait. Can you tell me which slides are you right now looking at? What's ahead? Is it?
What's ahead, sir?
Okay, and let me try next. Is it the same?
Yes, sir. It's the same.
Oh, then let me try another way.
Now it is presenter's note, sir.
Okay, now
Now it's the same, sir.
now.
Presenter's note. Presenter's note, sir.
Okay, wait. Sorry for
What
this
is
one.
edge computing?
Oh, now it's you can see the what is edge computing, right?
Yes, sir. Yes, sir.
Uh, Now, are you seeing the overview slide?
No, sir. No.
It will take 1 minute maybe.
I
Big
think there is a delay.
delay, yeah. Now you can see.
No, sir. Still the same. Edge computing.
Edge computing. Let me share my full screen.
Now it is overview, sir.
Oh, it's a delay. So interesting thing. Okay, now now we experience this delay, right? And for that, what we are going to talk about the latency. Okay.
And also, please switch to full screen mode, sir.
Okay.
It takes time to reflect, sir.
Okay. Let me share the full screen again. Okay. So- okay. Now you are seeing the team window, right?
Yes, sir.
Okay.
Hmm.
And now,
It's overview, sir.
okay. Now I'm switching to the presentation mode.
Yeah, perfect, sir.
Okay.
Okay.
Okay. So basically, yeah, this isn't AI generated. In short, that's what I wanted to say. Okay. So be curious. Okay. So the first topic is the what exactly is the edge AI, edge computing. Okay. So uh, why maybe these topics are covered in the syllabus because these are uh, not something new. It's coming from long time. Okay, so maybe some of the professors, those who are teaching the network computing things, those already know, but those who are not aware about this, that's why I started from the very basic and very beginning, because that ensure that you will not lost somewhere in the whole presentation, because we start from the very basic one, and that's what's the job of the teacher or the professor, that the student doesn't get lost during the lectures. Am I right? Yeah, so basically here is the overview about the network computing. Okay, so the architecture, we have a two kind of the architecture. The one is the client server and another one is the peer to peer. Okay, so basically here we have some examples of what kind of application or what kind of products which is using the P2P and the client to server. So here you can see the BitTorrent. So you download the BitTorrent file that is using the peer-to-peer, and the messaging is a peer-to-peer games. Sometimes it's a peer-to-peer, but sometimes it's also have a different version of the client and server mode. And in the client server, we have a video streaming. The best example is the Netflix. Then we have a web browsing, banking. So all are the client server architecture, and the other are the P2P. So I think this will help us to understand the basic difference of architecture. So where our interest is, so it's basically in the client server, and the client server leads us to the cloud and the edge computing. Okay, so let's move to the next one. So what exactly the cloud computing? So the cloud computing, you can see the diagram here. So we have a multiple devices, the user side devices and user device, that mobile, laptop, printer, whatever information it needs from the cloud, it we request from the end user that information, that goes to the that request goes to the cloud, and then from the data centers we got the response of that request, and that's how we serve we play the video, we serve the through the browser, we can get the information from the cloud whatever we request, right? So this is very if we want to explain the cloud computing in very layman language, then this is the definition. Okay, on the left side is something which is in the very professional way, if we want to explain, right? So I'm not going into the each and every word of whatever I try, written here. Yeah. Okay, so please feel free to ask and interrupt me, okay, whenever you have a question. So far, okay, can I move further? Please
Yes,
try
sir.
to make it interactive, okay. Okay, so
Yes, sir. Please proceed.
yeah, thank you. So after the cloud computing, the another thing is which we have is edge computing. Okay, so here in the cloud computing, what was happening is that we request from our end user device, that request goes through the cloud, which is far away from the end user or the end device, and then the request is processed in the cloud, and then we get the response. uh, Now this has a problem in the latency. The response time of whatever information you requested is a long, but it depend where you want to use the uh, uh, the cloud computing or the edge computing. That depends on what kind of product you want to design. Okay, which have a faster processing time, or the it is okay to have some amount of the latency, right? Then based on that we need to decide before we uh, before we develop a product, whether we want to go with the cloud or the edge computing. So edge computing is basically, instead our request goes to the cloud, it is get it get it gets processed by the intermediate at an intermediate level. Okay, that is, so what we did here is we moved our processing power from the cloud, that is the centralized one, to nearer to the end user, but still not at the end, not at the edge. Okay, it is still in the middle somewhere. But because of this, we can reduce a latency, and we can have a response fast enough compared to the cloud one. Okay, so you can see here that we so this one help us to reduce the latency compared to when an application run on the centralized data center. So every time in the cloud one, all the processing only carried out at a cloud level, data center level, not at the edge device. So that actually increase the latency. Okay, so let's move to the next one. So what is the difference between the edge and cloud? So cloud is a centralized data center with the high latency, high bandwidth usage. Edge is a decentralized processing near the data source, low latency. Cloud is ideal for a heavy computation and the storage like our Netflix, right? Because it needs a lot of storage and it has a heavy traffic because of so many users, right? So yeah, for that you can't use the edge devices, the edge architecture for the Netflix. So and the next difference is the edge is ideal for the real time and the low latency application. Can anyone tell me exactly the real time application? Uh, Let's say we need to think of the real time application. Any example? Please try to respond. Anyone? I'm not moving further. Am I audible?
Yes, sir. You're audible.
Yes, sir.
Yeah. At least give me one example. The real-time example where you can see the age can be used. Okay, I'm giving you the chance. Okay. Right now I'm moving further, but later I have a surprise for you. Okay, so let's move further. So yeah, so this here we talk about in detail why we exactly need the edge computing. So first thing is that reduce the latency for the time sensitive application. So time sensitive. So you can think of the smart car, right? Like the Tesla, you are driving the Tesla. It need information from the cloud, from the map, and that doesn't wait for so long to make a decision whether it need to move right, left, or need to move further or need to stop. So so that kind of application is very time sensitive. If it take too long, then Tesla have accident, right? So so that's why we need a low latency, save the bandwidth by processing data locally. That means you have a heavy traffic on the cloud side, but you have the edge computing, so that is already in the middle of the in the middle between the cloud and the end device. So the edge computing do the processing and only sends the a very minimum set of instruction or a minimum set of request to the cloud. Otherwise it handle the end device at at edge level on the edge computing level only, at the middle only, instead of going to the cloud. Okay, then another thing is the enhance the privacy and the security. Okay, so this thing the security and the privacy also can be carried out at the edge computing, that is the middle level of the architecture, right? And the next example is the smart cameras, autonomous vehicle, which we just now talked, and then the industrial IoT, right? So now in industry there are tons of sensors and the actuators and the control system pumps are there, right? So those you can't wait so long to get process the request or to take the decision, right? So for that, the edge, when you move the processing power near to the end device, then it become a faster response at the at the control system. Okay. Yeah. So the traditional computing, so here is just trying to understand. So data is processed at on the local machine. In the edge computing, limited scalability, the high hardware dependency. Sorry, this one is for the cloud one. Now in the edge era, the data process closer to the source. It reduces the latency, real-time responsiveness, right? And the time sensitive is important for the time sensitive application. And the modern edge ecosystem, you can see it is integrated with the AI, 5G, IoT. Now you see the 5G use case, right? Previously 2G, 3G, 4G, 2G, 3G, right? All the data, whenever we call, that goes to the data center, processed by the baseband unit, and then it goes to the cloud data center, and that then your identity is verified, right? Your SIM number, all those processing was carried out at very far to the end user. Now in the 5G brings the new architecture, which brings the baseband unit very near to the tower area. Okay, so now you imagine you are calling and you get very fast. You can connect with your friend or anyone, the other person on the other side, right? Very fast, because your processing is near to the tower area. So the antenna receive your signal, process into the baseband unit, your identification, the another person identification, all everything will be carried out at baseband unit, right? This is just an example, right? So that's how we make the response fast in with using the edge networking, or the architecture. So that is the whole purpose of the edge architecture. Okay, so here you can see we have this one, the center one is the data center, right? There those where we have a big servers and the storage area. And in the edge computing, what we did is, instead the phone or the smart buildings or the grids is directly connect to the cloud, it now connected to the edge gateways or the edge server. These are the small clusters we introduce, that is as a that we can call it as a edge, at edge level. So now the processing is done through the edge towards the cloud. Okay. Yeah, so you can see here there are so few examples. Okay, and here we can see that here is a graph also. You can see the low latency requirements. Okay, rail system, the connected cars. Okay, all this require the low latency communication. Then we go towards the medium latency, low, then the latency no issue, right? Then so when based on your latency requirement of your product, you can choose either architecture. Okay, so this is very basic fundamentals of the computing, network computing with the edge and cloud. Now the next topic is, what is edge AI? So just now we talked about the cloud versus edge. Now the next topic is the edge AI. So edge AI refers to the deploying artificial intelligence model directly on the edge device. Now you see here what we did first. At initial stage, we were at a cloud. The processing was carried out by cloud. Then we move one step ahead, right? Further, then we put the processing we move the processing power near to the device. Now in the edge AI, we are giving the processing power to the end device. Okay, so that is what about the edge AI. Okay, so this why exactly we need the edge AI. Okay, so today you see we have the low latency requirement. Now even the communication with the edge server is not enough, or it's not it doesn't have enough speed or the communication that which is required by the connected car. Okay, so we need a more processing at very near to the edge device. So that's where, and then that is also should be we want to add the intelligence which we were carried out, the processing we were carried out at a edge or the data cloud. That processing power we want to give it to the end device. Okay, so here you can see the so when we add this edge AI capability to the device, then it can come over with low latency, right? The privacy and the offline capabilities. That means even if the device cannot able to make a communication with the edge or the cloud, but it has enough intelligence that it can make a decision on the spot, right? So those are the capabilities we are introducing using the uh, edge AI technology. So the examples are the smart cameras, wearables, autonomous vehicle. Now I give you one example of the smart cameras. Previously, you uh, uh, the screen is visible, right? Any issue? Okay, I'm moving. So I'm giving you the smart example for the smart camera. So previously, what was happening that smart camera function was only limited to capture the image and to send it over to the cloud over the high speed interface like the ethernet. You connect it with the ethernet or any USB, or you just display it to the with using the HDMI or the display port, right? So that was the very basic function of the camera. Now what exactly the smart camera is doing, we are adding the intelligence to the camera. So camera can detect the person, detect the mask, detect the helmet, right? Those kind of thing, that intelligence we adding in the camera. So now you think that you can imagine that now camera no need to send the full image or the full video, right, to the cloud. Instead of that, it just need to send some flags. Okay, that okay, camera detected one person is without helmet in the plant. Okay, so that is the one piece of information need to send to the cloud instead of sending the whole image or the whole video data. Now you see how much bandwidth we can save of the cloud from the end device. Okay, so that is the very basic example of what exactly the cameras can do, right? There are many other applications which we can see further, but this is just to give idea how much we can save the bandwidth, the power, and the usage of the hardware. Now we no need a high speed ethernet. We can remove the high speed ethernet with the low speed one. Only 1 gigabit rate is required. If you transferring the whole image, then you need a 10 gig, 25 gig, 50 gig, right? So that's how this edge AI capability actually make the device intelligence, as well as it saves the resources also, right? Then the next example is the wearables. We have the smart glasses, right? It can show you can see the whole display inside your smart glasses. Then you have a smart watches, All those things have AI capabilities, right? And autonomous vehicle, we already talked about it. So now the question will come. So what exactly the difference between the edge computing and the edge AI? Okay, so here you can see the definition wise is processing the data near the source, and the edge AI is actually running the AI model directly on the edge device. Then the purpose is to reduce the latency, bandwidth uses, and the enable intelligent decision making locally. That means the camera can decide what exactly it can detect whatever you want to detect from it, and it just send a single piece of information, small piece of information, instead of sending the whole frame or whole video. So the next thing is the data handling, the raw data. Yeah, so in the edge computing you see here raw data. So raw data is nothing but your video frame, and the AI enable analyze and interpret data locally. That is your small piece of information that one person didn't have a helmet on his head. So you can see how big the difference is here in the data handling. So here are some example which we just now already discussed about that, right? And you see the internet dependency. It's very, here is a low, and here in the AGI is a very low or none sometimes. And here are some use cases. So IoT, smart factories, autonomous vehicle. Uh, okay, the autonomous vehicle, some, so it's actually we have this use case in the AGI also and in the edge computing also, because not all functions are the AGI. Some are the edge computing and some are the AGI in the autonomous car. Okay, so now it's time for exam, right? So try to be more interactive, right? Try to respond it. Okay, can anyone tell the first uh, can answer for the question? Which one is the faster for the real-time task, cloud or edge? I don't want to make it boring lecture. At least Dr. Shruti, you can collectively, you can respond me. Huh? Uh, the answer for the first question, is it a cloud or edge? You can see my screen, right?
It's edge, sir.
Edge. Okay. Edge. Okay. Edge. Then next one. Uh, any guess? Okay, I give you a hint. One of the shopping website. Start with the letter A.
Amazon.
AWS, sir.
Yeah, Amazon Web Service. Okay, then the next one, is the cloud computing centralized or decentralized? Any guess? Yeah.
Decentralized.
Cloud computing is a centralized. Okay, which one reduce the latency, cloud or edge?
Edge.
Edge. Correct answer. Then name a device that use the edge computing. Just now we see so many examples.
Autonomous cars.
Autonomous car, yeah. So yeah, who is the ranker?
Ramaya Pete.
Okay, so here are the answers. So the first one is the edge computing, next is the AWS, then another one is the AWS is very famous, but there is a Google Cloud also. It provides similar cloud services. Okay, then the centralized one, then the edge, reduce the latency, and smart car, autonomous car, same thing. Okay, so far any question? No. Then here I would like to show you some the trending edge AI platforms. Okay, so here are the some links. Okay, so we have an embedded system developer kits module from the NVIDIA Jetson. NVIDIA Jetson is a very famous platform right now. If you want to develop your product with the edge AI capabilities, then you can use the NVIDIA Jetson platform to prototype your product. And then after successful pilot project related things, after the successful prototyping, we can convert our prototype into the real product. Okay, then we have Intel's Movidius Neural Computing SDK this platform. This one to mimic our brain computing into the hardware. Then we have a edge AI solution by the lattice semiconductor, so which use the low power FPGAs to develop the edge AI products. Then we have the FPGA AI suits, and TinyML also popular, just like the NVIDIA Jetson. Okay, so the disclaimer is these are not the advertisement or marketing. This is just for sharing information and the knowledge sharing only. Okay. Let me go to this one. Okay, because why I open this one is because this one has a good example of the flow. Okay, so you can see here that let's say you want to add a edge AI capability in your device, then the first step is you need to develop a prototype, right? So what exactly that prototype flow you need to carry out is that we should okay we should have a pre-trained AI models. So right now we have a TensorFlow Lite, the Onyx, Keras, right? These are the pre-trained AI models. You can get them, get all the models whichever you want to use from the vendors, right? And then we have a Open Rhino model optimizer, which convert a pre-trained model into the FPGA to make it fit into the FPGA. And we have the FPGA AI suite. So this AI suite actually help to generate a design for the Quartus tool. So basically it is converting your AI model into the RTL, and that RTL will be synthesized by the Quartus tool, and it will be downloaded. The bit binary file is downloaded into the FPGA, and that you can use that whole board with the FPGA to mimic the behavior or to check all the specification and the requirements, all the functionality, while you have this whole model, edge AI model inside the FPGA. So here they explain in detail. Okay, I think we not going further down inside this one. I think you guys means later anyone is interested, then they can have a look at this one. So let me zoom it here a little bit if possible. Yeah, so basically this one is explaining how the QSys of the Quartus tool is used to convert our AI models into the system system design of the FPGA, and that is converted into the custom RTL and then loaded into the FPGA. Yeah, so that's how you can use the any FPGA to prototype your AGI capable product. And Jetson, okay, Jetson also similar to this one, but it is not an FPGA. Okay, so you can see here, this is the Jetson, the features and the architecture things. Okay, so these are the platforms you can use. You can see the boards are here, which has a capability to run the AI models, and it can have a different interfaces, like if you want to run it with the PCI, USB, Ethernet, then the video application you want to run with the cameras, displays, MIPI interface, all those things you can attach with these boards and you can prototype your product. Okay, so let's not go further into this one. Let's move to the next one. Okay, so you can see another one is the this one is a very important one. You can see here is the pure FPGA, the latest one, Quartus one, right? And here is the pure ASIC, but there is a combination of ASIC and FPGA. So you can see here, this is the architecture of the ASIC plus FPGA, that is called as the embedded FPGA. So you have a hard blocks, you have a CPUs, hard CPUs, hard macros you already have into the silicon, but you have a configurable part as well on the same die, or maybe you have a chiplet architecture. Okay, so this embedded FPGA part you can configure it as or program it as per your need. So yeah, sometimes with the ASIC, what happen is that you need to use the go with the data sheet, whatever they ask you to use the pin flexibility, all those things is not with the user. The FPGA gives you that flexibility. Let's say you want to process the CPU data, that then after that data you want to transfer it to some other protocols which interface is not available with the SoC. Okay, so you want to transfer it with the custom protocol also using this FPGA the block inside the die. So this is the embedded FPGA, which is widely used by the edge AI devices. So now we are moving towards the actual topic, the low power design. What is the role of VLSI in the enabling the edge device? So it actually enables the compact, efficient hardware for the AI task. Custom AI accelerators, low power chips are built using the VLSI techniques. Support the real-time inference with the minimal power consumption, and integration of memory compute control unit on a single chip. So all these capabilities, because when you design the edge AI product, there are some specification. Just now we talk about the latency, bandwidth, and all those things, right? And after that, the very critical aspect of the product is, or the specification is, the low power, because mostly the edge AI products are the battery operated. So when it is battery operated, it is it is obvious that we need to save the power. Okay, our ICs, our FPGAs should not be the power hungry. Okay, so we need to make sure that it use the minimum power with the high performance. So this is the role of designing the ICs or the FPGAs, which can enable us to design the low power AGI products. Okay, so here it is written basically what just now I discussed. Okay, so you see here the AI models on the resource constrained edge devices. Benefits are the energy efficiency, fast response, enhanced privacy. The challenges are the design complexity, thermal management, scalability. Scalability also matters. Let's say you design a product which is not, there is a noise. Yeah. So, hello. Uh, can someone please check whose mic is on? Okay, thank you. Still, it is coming. Okay, so scalability is a very important aspect when you design a AGI product, because let's say you design something which is not scalable, or which is just become old after 1 year, 2 year. Okay, you cannot use that product again, right? Or the future requirement from that aged AI device is, we haven't considered that future requirements. Okay, so that's where the scalability comes. So whenever we design the ICs or the FPGAs for the edge AI, then we need to make sure the scalability also. Okay, so the future thing is that it's a AI specific VLSI architecture for the edge computing. So far we were designing the ICs for the high power, uh, sorry, low power with the high performance architecture. Now the additional terms added into the architecture, VLSI architecture, is the ES specific. So what are the VLSI design consideration for the edge AI device? So first is the low power consumption, because it's crucial for the battery power edge device, energy efficiency, optimize the power performance per watt. And what are the techniques for the low power consumption? So the first one is the clock gating, power islands, near threshold operation, use the specialized AI accelerator that are the NPUs, DSPs. Okay. Uh, the techniques we further discuss in detail about the techniques. Okay. So right now I'm not going into too much detail about that. The next one is the compact area. Okay, edge device are very small devices. Okay, so we need to make sure that our ICs are having a small footprint. Okay, so we can make it fit into the small devices. And the efficient layout and the routing strategy, that one also we'll discuss later. So here is the low latency, so real-time processing. So basically why we need a low latency, because we need a faster response time. And for that we need to minimize the memory access delay, because the memory we have the FPGA or the processor, and which has the external memory. Then to process the request, let's say it needs the data from the memory, then that memory access time or the delay should be minimum, right? So those are the things we need to take care. The next thing is the on-chip intelligence. So support for the AI inference directly on the chip. That means you can you can able to deploy the AI model directly on your chip. Okay, which include it should include the hardware for the CNN and the RNNs and the transformers. So these are the neural network things. Okay, so for that you need a special hard macro blocks. It should be there in your silicon to process. If I want to drive the neural networks onto the IC, right? Then we should have these blocks already there into the silicon. Then the next is the memory optimization. So here we have the SRAM efficiency, reduce the DRAM dependency. So and employ the quantization, pruning, and the compression. So these are the memory related operations which we need to take care during the design. And then the security and the privacy, right? So the encryption. Now you think that let's say I want to do the security operation, the security check operation at the device level. So then I should have the capability in the hardware for the encryption and decryption of the security keys. Okay, so for that we must need a algorithm and the capability at the silicon level to decode that. And the last point is the scalability and the flexibility. So the silicon should not be designed in a such a way that it just run a few models. Okay, it should be a dynamic. It should run a multiple models. Okay, it should not be specific to some models only. Okay, and the modular design for the future upgrade. So future, whenever we need upgrade, then we can be able to do it without designing a new product again. Yeah, so the question is why low power? So the first thing, battery powered, right? So you can see the wearables, drones, sensors, all mostly are the battery powered, and which require the long time of the operation. If it's power hungry, then it won't work for so long time. Yeah, then for the remote and the harsh environment, yeah, so this is another thing. Let's say our device is installed in the remote areas where we need to rely on the, let's say, solar or any wind energy. We don't have the grid there, so for that we need to make sure the device use the low power, and uh, at the same time it provides the same functionality. So the next is the thermal management. Okay, so high power leads to heat, which can damage the component or the require the bulky cooling. So this is also an important parameter or the requirements or the consideration we can take care at the silicon level when we design in the backend designing. We can take care of this part. The next point is the real-time performance. Okay, so efficient power usage allow the faster processing without draining the resource. So, and the important for the application like the autonomous vehicle and the industrial robots. And the environment impact, reducing the power consumption contribute to the greener, more sustainable. You need a less battery, less size of capacity, less capacity of the battery. Instead of you need 100 ampere battery, you can use with the 50 ampere if your product is designed well with the low power consideration. So that is also saving. We are make it more sustainable technology. Now here we have the slides is about the role of FPGA in the edge computing. I think we pretty much carried out these things because uh, if you are teaching the VLSI course, the first thing is that what is the difference between the FPGA and ASIC, right? So I think no need to go further because you see the FPGA have a more reconfigurability. The ASIC are the specific one. FPGA used for the prototyping. ASIC is the final. Let's say after our prototype is successful, then you go for the ASIC. So these are the very basic, well-known FPGA ASIC difference, which are also important for the edge computing, edge AI computing. Here is the same again, the FPGA and ASIC difference. Okay, so that the it's a very foundational difference which again matters into the edge computing. Okay, so here we deep dive into the low power basics. So when we say low power, so we need to find where exactly the power is drained or by which component. So the first comes is the CMOS MOSFETs, right? Our transistors. So in the CMOS, this is the I just consider the CMOS here. Okay, so we can see the static and the dynamic power. So we are not going into too much detail of these things, but here we can see the total power dissipation is the dynamic plus static. So dynamic power depends on the switching, glitching, and the short circuit power. Static is depend on the punch through. Then this one is the drain induced current, I think, and the threshold, sub threshold gate tunneling, then the hot carrier injection, PN junction current. So these are the important factors which contributing to the static power, and these are for the dynamic powers. So when we talk about the low power, this is the very basic thing which we need to consider while you designing a IC. Okay. Now here is the difference between the dynamic power and the switching power. Why we need to consider this? The static power is actually comes when you are at the hardware level. Okay, when you designing a silicon, then at that time you need to make sure the static power of each, static and dynamic both power consideration, how much power it is, which will be taken by the CMOS, right, when it will be functional. So here is the basic difference between the dynamic and static power. Now where we most interested is the control methods. Okay, so you can see here how we can reduce the dynamic power and the static power, right? So the first thing is you can see the clock gating. Then here is the dynamic voltage and frequency scaling. Then reducing the switching activity. Let's say we don't need a flop to uh, let's say we get the information from one flop, right, and that information we need a once in a 1 minute. Okay, but it is keep toggling for 1 minute, right? Then it is no use, and it is increasing your dynamic power. So at that place, either you need to stop that, uh, provide the clock to that flop and the power also. Okay, then you can save, we can save the dynamic power. And the power getting, I just now just said, right, that power we can also control the power. Okay, and there is we can also change the VDD, the voltage to the flop. Okay, we can work on we can work on a different voltage level, and we switch dynamically the voltage level after in the chip. Okay, so yeah, so you can see here the impact on the design, right? So it's a dominant in the high frequency design, because high frequency uh, we have so much toggling of the data over the flops, right? So it directly increase the dynamic power. And the static power one is when we design the silicon, right, we need to make sure what kind of technology nodes we are using and how power hungry they are. Okay, so these are the basic difference. So the next item is that the power, performance, and the area trade-off. Okay, so here either you can you can choose one out of three. You want to save the power at cost of performance, area, or you can design a product which has the balance of power, performance, and area. Okay, so this is the very basic trade-off in the VLSI design. Okay, because all three are connected to each other. So here we can see how the power is power versus area, right? Because the reducing area can lead to the high power density and the thermal issue, because we are tightly packing the transistors in a small area. Okay, so here then the next is the power versus performance. The high performance usually requires a higher clock frequency. That means more toggling at the flop level and more dynamic power. So so to tackle out those things to reduce the dynamic power, then there are some techniques that like the dynamic voltage and frequency uh, scaling, then the parallelism pipeline to balance the power and speed, reducing the frequency, lower power but increase the latency. All kind of techniques. There are some techniques which we can use to get required performance either in power, performance, and area. So now we talk in detail about the few techniques here. So first is the clock gating. Okay, so what exactly is the clock gating here? You can see that we have a one flop here, and it is a there is a AND gate here, right? So what we will do here is we do the clock gating actually. So let's say a output we don't need an output from some flops, then we can shut off the clock uh, goes towards those flops. Okay, so that will stop the unnecessarily switching at the flop level. So why it is important? Because this one reduce the dynamic power consumption, right? The clock getting helps to optimize power, especially in the battery powered uh, and the thermally constrained system. So there are two types of the clock getting: one at a logic level getting and the clock level getting. So we can introduce the clock gating at the RTL level. Okay, there is a one example here, right? And another one is using the dedicated clock gating cells or primitives. So when you are designing a SIC IC, right, then from the technology node you will get some cells, the specific functional cells which are used. Some are for the power gating, some are for the clock gating. So that cells or the primitives we can use in our design when we are in the front end stage of the IC design. Uh, so here is one example. Okay, let's say we carried out we have implemented the clock gating. Uh, uh, we have implemented the enable signal for the flop, because this flop output only needs when the enable is up. So the synthesis tool is intelligent enough to identify this enable behavior and that convert into the clock getting behavior. Because whenever the enable comes, then only we need this clock to run this flop. Okay. Otherwise, this clock is unnecessarily driven to this flop when the enable is not there. So these are the tool level optimization carried out if you instruct the synthesizer tool to do that. Okay. Then another concept here is the power gating. So in the whole chip, let's say some are the functions we don't need for some time, right? Then what we need to do is shut down that whole block or the hard macro, uh, disconnect it with from the main power rail. Okay, so no power will goes uh, to that particular area or the particular section in the chip, and that's how we save the power. Okay, and uh, for the FPGA we have some power analyzer tool. Okay, so some FPGAs have that feature that you can shut off some of the functionality if you don't need. Okay, and in the ASIC there is a intelligent block we can introduce, that is the internal power management controller. So that one will check continuously based on your application, that whenever we need to shut down some blocks, cut off the power, then it will control those things. Okay, the next concept is here is a dynamic voltage scaling, voltage and frequency scaling. Okay, so this is a okay, if you know the MOSFET theory, right, then we have a if we reduce the voltage of the drain operating voltage of the CMOS or the MOSFET, right? That one reduce the overall power, okay? Because the static power is there, dynamic is there. So this concept is actually help in the designing, help into the designing the chip which have a multiple VDD. Okay, so some ICs block are running on 1.8 volt, some are running on the 2.5 volt, some running on the 5 volt. Not it is not necessarily to run all the blocks at 5 volt. Okay, we don't need that. So the IC design should have a capability to change the dynamic voltage whenever it required. And the another uh, factor is the frequency scaling also. Let's say sometimes we need to run our edge device at 100 megahertz. Sometimes we just need a 10 megahertz frequency to run it. Then that drastically change the power requirements. So this is the very important feature where we can introduce into our IC design to to make it low power. And then there are some, let's say you design the whole system, then you can either have it internal power management controller, or you can have a external controller. So the external, where we are driving the power to the power pins of the IC, right? At at that pin, we can reduce or dynamically change the power. And the PLL also used to control the frequency, input frequency to that IC. So this is all about the dynamic voltage scaling, voltage and frequency scaling. Now, this part is actually at the designing level. So when we design the RTL, right, what things we can take care. So here is the few important parameters, like the low latency. We design a block or the RTL which has a low latency and high bandwidth. Okay, optimize the IP blocks for the AI task, like the DSP, memory controller, all those. Then the reduce the switching. Some flops we don't need to toggle it. Then just try to design in such a way that it stop toggling and save the dynamic power. Right. Then we design. We can use minimize the use of LUTs, flops, DRAMs, because I give you one example, BRAM, right? BRAM is a hard blocks. It's a hard memory into the FPGA. Let's say you need a 32 location of the memory, but the BRAM is having a maximum capacity of 2K. So even if you choose the if you even if you need a 32-bit location, 32 location, but you are wasting the 2K memory for that. So the whole 2K memory is getting the clock, getting the power, right? So instead of that, you design your own small memory using the free flip-flops available in the FPGA. So that's how you can save the power, right? With the small and only with the small memory only. No need to use the hard macros. Okay, so and some are the techniques also. Yeah, some protocols. So we have the high-speed protocols, right? The USB, PCI, Ethernet. They also the Bluetooth, Wi-Fi. All these protocol have a low power mode. Okay, so you consider your mouse is using the Bluetooth. So whenever it is not active, you are not moving the mouse, then it goes into the low power mode, and that's how it saves the power from your battery cells. Otherwise it will drain out in 1 month if it keep continuously connecting and communicating with your laptop or the PC. So this is very basic example. That's how we can at the protocol level, how we can save the power. Okay. So same in the USB, PCI, Ethernet, all the protocol have a low power or low power modes. And we can use the data processing techniques like the parallel and the pipeline structures. Okay. And when we combine it, then it become a pipeline parallelism for the AGI. So it has a power of parallelism processing and the pipeline processing. So that combining both the techniques, which give us a faster processing capability. Yeah. So far we talked about the front end side. Now these are the techniques we can change on the we can introduce at the backend design level. So that is the physical design or the layout time. So we can add the multiple VDD implementation that is just now I talked, right? It has a 3 or 4 power rails to the all blocks. Whenever we need a power, we can the blocks can switch from 1.2, 1.8 to 2.5, 5 volts at dynamically. Uh, okay, so then the power getting we already talked. So mostly here the difference is the low power cell also we talked, right? And the floor planning. So floor planning also the important aspect while we designing at a physical layer. So you can see the optimize the routing to reduce the IR drop and dynamic power, right? Then the place high activity blocks near power source. So sometimes we design in such a way that 2 blocks need to communicate, but both are at the different age of the device or different age of the die. Okay, then it need to utilize the all power rails, all clocks, all the routing uh, across the whole die, right? That is the wastage of the power. Okay, so these are the backend techniques. More and previously we discussed about the far end, and here are the future trends and research direction right now. So here is a very interesting topic. Here is the in-memory computing. So I try to explain you very short, right? So let's say you have a processor and external memory. Now processor need to do some summation of 2 data, and that 2 data already stored inside the memory. Okay, then the regular the normal CPU, what it will do, it will fetch both the data, get it inside the CPU, do the summation, then get the answer. Now this is in this technique what CPU is doing. CPU just ask a memory location, the memory controller, that I have a 2 data stored at particular location. You do the summation and give me the answer directly. So that is what the in-memory computing. So right now this is the active research area where the people are doing research, right? So so you can see here how we can save the resource from the CPU, okay, and the memory itself can do some of the computation and just give the process data to the CPU. Then the neuromorphic architectures, right? So this is nothing but we want to implement the intelligence just like our brain into the hardware. Okay, and the next one is the AI ML assisted power optimization. So low power also can be a AI ML assisted. So for that we need to design AI models. We need to do the machine learning. So when we need a power, when we don't need, what are the blocks which is running unnecessarily, all those optimization. When we have a design, full design, we run the ML or the AI to identify the areas. Okay, so that's how we can use the AI ML. Yeah, so okay, so here are some interesting examples of the Edge AI designs. So up to this slide, I already covered the low power things. Now I'm moving towards the final stage of the PPT. Okay, so here is the Edge AI design examples. You can see the person has wear mask, helmet. This processing can be carried out at a camera level, not at the cloud level, not at the processor level. Camera just send the some information that this person, only the ID of that person need to send to the processor. Then we have a tumor related analysis, right? So from the image here, you can see AI or ML can detect the cancer or anything, right? So those kind of medical use cases are there. Then the road safety or the rules following on the traffic signal controls, all those can be carried out with the AGI. Another example you can see is very interactive one. Let's say you have the device that will check your posture while you are doing the exercise and give you the feedback instantly. Okay. The another one is the use case of the agriculture. You take a picture of the leaves and you see the dot dots. Okay, so then it will help assist you what kind of disease or what kind of issue is with your crop, right? And you can take the corrective actions after that. Okay, so here are some interesting edge AI use cases from the ST microelectronics and IoT solution here, right? So you can take a look. Okay, so yeah, that's all from my side. Any question? We have how many minutes? Oh, 4 minutes. Any question? If no, then I don't waste your 4 minutes. I have something to tell you. Okay, so you can see here I write down something experience a teacher student you. Uh, I I am very happy that you guys have a role of a teacher or a professor because it is very important in the student life. Because I got the professor and the mentors; those were very kind and uh, helping me cover up my mistake and giving me another chance, right? Discuss me what are the problems or with the projects, with the understanding or with the any issue on the work or the during the college or university time also. So uh, the professors or the teachers roles is very important. It is not just any ordinary profession. It has so much responsibility because you can make or break a student, right? So I hope you all are doing a great job, right? uh, because I uh, I just close my presentation with one of the experience, right? In the university, uh, I got in the master, I got the one professor from the Hyderabad. He's still living in Hyderabad, but whatever he taught us about the IC fabrication, Sokolsky growth, then the float zone, all those things, physical vapor deposition, I can tell you that I can explain today also after 10 years in detail. Now that is not because I I learn it or not because of I read it well or I understood it well. That's all because how my professor explained from beginning to the end. He maintained the chronology from starting from silica to the IC. Now the whole life I can't forget that part. I can explain anyone and explaining in the layman language. That is also important thing. As a professor, as a teacher, you my professor come down to my level, our level, to the students level, and then explain. So that is very important and things in the professor's life. And I salute those are the PhD holders. I, I actually started PhD, but somehow left, got the practical knowledge, but didn't do the paperwork. And that's how I didn't get the degree. But I salute those who completed the PhD, yeah, and those who are pursuing also. And those who are not pursuing, but they are the professor. So yeah, So that's all from my side.
Sir, we sincerely thank you for taking the time out of your busy schedule and deliver us such an insightful lecture, sir. Thank you so much.
Yeah, actually, I would say thank to you. This opportunity for me to say, yeah.
Thank you, sir.
Eh,
Thank you.
So we started late, but we complete on time.
On time.
Finish it on time.
And
Any
even the
question?
latency has been reduced, sir. I couldn't
Huh?
find any time lag between the slides.
Oh, okay, okay. Actually, I switched from two screen to one screen. Maybe, maybe because of that. Any question? Or yeah, we can move to the next one.
Any questions from the participant side?
If no question, then I must need a feedback.
Actually, we are collecting the feedback at the end of the session, sir. If needed, we'll be posting it to you. Or
Okay,
otherwise,
okay.
if you need any oral feedback, you can take it from the participants, sir.
Okay, sure, sure. Okay, yeah. Thank you so much.
Yeah, thank you, sir. Thank you so much.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah, moving forward, our second session is bound to keep the momentum alive. We are privileged to have with us Mr. PVSR Bharadwaja, sir, who will shed light on advanced FPGAs. Mr. PVSR Bharadwaja is an FPGA designer engineer at GRL Technologies Private Limited, Bangalore. His current role centers on the development of physical layer for DisplayPort 1.4a and 2.1a, where his primary responsibility is writing RTL code. Bharadwaja sir, who earned his master's degree in 2015, is proficient in Verilog and System Verilog with hands-on experience in managing timing constraints and clock domain crossing. He is skilled in utilizing development platforms like ZC702 and Area 10 and is proficient with design tools including Quarters and Vivado. Furthermore, his expertise includes leveraging VC Spyglass for comprehensive error checking, ensuring high quality designs through linting, STA, and CDC analysis. Bharadwaja is driven by a desire for continuous learning and rapid skill acquisition. Sir, we invite you to take the session forward, sir.
Yeah, thank you.
Thank you.
Yeah. Hi, good afternoon, everyone. All the distinguished people and all. I think a few people must be in a very higher positions than me, and a few people must be having a good knowledge than me. But today we will be discussing about something new, what's running behind this FPGAs. And if there is any problem with if with my discussion or you are unable to understand, please stop me in between. It's not a problem. Okay. So I think it's the back-to-back session for the participants. Is it okay? Shall I start? Can I? Yeah. Anyone from the
Okay, sir.
participant? Yeah. Okay. Hi. So first, let me introduce myself. You must have heard something from the ma'am, whatever she said about me. But before starting, I wanted to just discuss or tell about me. And by the way, are you able to see my screen?
Yes, sir.
Is my screen visible?
Yes, sir. It is visible.
Yes, sir. Yes,
Yeah,
sir.
fine. Thank you. Thank you. So whenever initially just like a prologue or something of about this session, Nagendra sir is actually my faculty. He taught me. He taught me when I was in my masters. He came for us for a couple of subjects in this VLSI. And when I received a call from him, he said, Bharadwaj, I want my participants or my audience to have a wider approach over how you are implementing the AI tools, AI on the FPGAs. So this is the name of the workshop, and I was really immensely very happy to share this knowledge because nowadays so many people approach us, but everyone will tell like, sir, please tell what's already there. Tell us about how to resolve the timing issues. Tell us about how to resolve the CDCs. And okay, fine, not a problem. Please mute yourself, please, someone. So when I heard that, I was really very happy, and I said, sir, I can promise you, I will be telling you a few things which are really running in the industry. So I've been associated with an industry since 2 to 3 years only, and earlier I have almost 4+ years of my teaching experience. I worked as assistant professor, and I was mostly involved in designing, means in making the students design in Verilog and in system Verilog and all. And we also started a digital design laboratory. And later I was continuing my research there. I had a 2+ years of research experience, but unexpectedly I haven't completed my PhD. But I got a very good opportunity at Granite River Labs Technologies. Our company is Granite River Labs Technologies as of now. So the main motto of our company is to just deliver a very good testing platforms for DisplayPort, USB-C, USB PD, all these things, which are really good. See, we are really working on the next edge technology. The next technology which you will be using today, tomorrow, will be tested by us today. So to test that, we require some efficient mechanisms. Means we require to implement that protocol, and we require to tell that, yes, this technology is very good. It's great. Okay. Means for suppose if you are using USB Type-C cables, for the USB Type-C, you need a tester. So to test that, yes, this USB Type-C is very good. So we develop that testing mechanisms. So to develop those testing mechanisms, we require the complete understanding of the protocol, complete understanding of the wire lengths of this, whatever the things. And we require immense knowledge rather than implementation. We should be able to understand if there is some error. We should be able to detect that error. That is what we are doing today. So whatever the USB QI chargers from the Apple, the Qi protocol, means the wireless charging protocols, the testing mechanisms and all from the Apple, and the USB Type-C, which has been the standard of the complete world nowadays. The testing mechanisms for that, the testing mechanisms for the DisplayPort, DP, we call it as a DP 1.4a and 2.1a. We have successfully implemented, and we have been testing this DP protocols, and we have delivered it to our customers on a record time. And we are now working on the DP 2.1, the DisplayPort 2.1a protocol, which requires, means almost there will be a different mechanism which will be involved, which will be too good. So we are working on the standard technologies now. Okay. So, and unexpectedly, I haven't completed my doctorate, means I left it in between, but I started working on the same image things only, image, video processing, all these things. We have worked on a very extensively. Okay. So that is about myself. Okay. Fine. So before starting the session, I can take this session in two different ways. One way, I have prepared some 49 slides. Okay, excluding all these things and all, it will be somewhere near to 45 or something, 45 slides. I can take each slide for 2 minutes and I can explain you and I can leave the session. That's one method. The second approach would be, as you people will be enthusiastically, you will be teaching with the students, right? Because to gain that students' attention, you take some live examples and you teach the students. We salute to every faculty out here, because you will be trying to imbibe a very good knowledge basics into the students. So in that way also I can try. So I always chose the second way. Being a faculty in my earlier days, I chose the second way. So first of all, I have written something in the agenda like it's partial reconfiguration, dynamic reconfiguration, hyper retiming, hyper pipelining. But first of all, let us try to understand why do we need all these things. Okay. Because today our concept is completely related to the AI, the artificial intelligence. In order to implement the artificial intelligence on the FPGAs, whatever the existing FPGA, we consider everything to be a static. What does it mean by static? Means once you program it, again to reprogram it, you need to just turn off the board and turn on, or it was in the earlier boards, not in the present boards, or you need to again reprogram the board directly. Means if you are taking anything, you need to generate that bit stream, you need to combine that with the required firmware, and you need to also add a few interrupts that can be done by the software. So all these things will be combined into a single file, and this file will be sent to the FPGA, where the FPGA we will be able to run on. This is the actual static method which we are using in the FPGAs, but this method is outdated. Outdated in the sense, still we run in the similar fashion, but there are very new methods in the market where you can run it in a still more efficient way. Is that okay? So now let us try to understand what is this efficient way which is now in the market. Now let us take, there is a hall, there is a room. Let us take, there is a room. The same room in the morning, I think when we were means if you are having a very less space, for suppose if we are living in an 1 RK flat, for suppose, the same room whenever we are eating, it should work like a dining hall. The same room whenever we are sleeping, it's like a bedroom, and whenever we are actually doing our work, it's an office room. So the same room, we will be just moving the things here and there, and we will be changing it dynamically, whatever we require. For suppose if you are sleeping, you will just lay your cot. For suppose if you are eating, you will just bring out your dining table. If you are doing some office work, you will bring out some table and set up your laptop, and you will be running your work. So the same room can be used in different ways. That's the main motto. Means the same FPGA should be able to be used as differently, very differently. How can we do this? For suppose if you are having a room, every time we cannot change the complete room, right? Am I correct? The room dimensions will be same. The room end to end dimensions will be same. But we are going to make a few changes inside the room. We are not going to make any changes from outside of the room. I hope you are able to get my point. Am I clear? Yes? Anyone? Am I clear, or is the example okay? Do you want one more? Guys, please. Anyone? Sorry, fellow professors. Okay. I hope I'm good till here. If you are having any doubt, please you can stop me anytime. It's not a problem. So in the same room, we are not going to make much changes. We are going to make some changes inside the room. Outside of the room, we are not going to make much changes. The room size and all will be same. So this is the idea of reconfiguration. Reconfiguration. The name itself is suggesting you. Okay. Then what does it mean by partial and what does it mean by dynamic? In the next few and a couple of slides, we are going to get an idea. So a few years back, when I met a particular professor, means he was a professor earlier, he completed his doctoral and he is now working for a very good firm, Qualcomm, where his main target is the same, whatever this one. I have learned everything from him. Him in the sense, he used to guide me a few years, 1 year completely we traveled together, but unexpectedly something did not work out and I was not interested in that research area, and I again came back to the industry. So in that particular course, he has given me an example. He asked me to do something like, Bharat, I want an FPGA. In the same FPGA, whenever I want an addition operation, I want that particular module to add a few things. Whenever I want a multiplication operation, see, addition requires two inputs. Am I correct? Addition mostly requires 2 inputs. So whenever in the same way, means 2 inputs and 1 output addition. I'm just telling as an example. Please don't feel it's in a high level. It's a very low, pretty low level example. Please try to understand. Okay. And whenever I wanted to subtract, again, these are the two inputs. The inputs are two only and the output is one. The inside operation is different. And again, if I want to multiply, the inside operation is different, but again, it's the two different inputs and one output. And by the way, just pardon me, two different inputs in the sense it can be 8-bit, it can be each of 8-bit, each of 16-bit, each of 32-bit. It can differ. Just as an example, I'm just taking this. Again, if I want to divide, I can divide. You require again the two inputs, one dividend and the divisor, and whatever I want output as only the quotient. I don't want the remainder. So this is the functionality I wanted. I said, okay, chalo, very good. It's very easy, sir. I will just implement an ALU. But he gave me a task. I want the area to be very common. Whatever the maximum area out of all these four will be taking, I want only that area to be consumed inside the FPGA. Means inside the FPGA, as every one of us know, we will be having some CLBs, LUTs, and if you go for the Intel Quartus, Intel based tools and all, you will be having LABs. Okay, so like that. So he asked me that area should be constant. At that time, I was really baffled because I don't even know what to do. At that time, I was introduced to this idea of partial reconfiguration. So in fact, that example really helped me in understanding the partial reconfiguration better. So as I can summarize you, the addition, multiplication, subtraction, and division inside the FPGA with a minimal area. Means whatever the maximum area which is occupied by any one of these operations should be the area. The area shouldn't be high or shouldn't be low. So this is the idea of partial reconfiguration, as I already said. Okay. So now let's go into what does it mean by dynamic. I will tell you, because once you can understand the partial reconfiguration, you can understand dynamic at a very greater understanding. So this is the partial reconfiguration. What does it mean by the partial reconfiguration? As I have already mentioned, it's a dynamic ability to reconfigure. Okay, but just try to observe the slide. In that slide deck, you can see on the right side that I have just highlighted an area. A small area has been highlighted. And persona A, B, and C are nothing but the addition. Let us consider if they are addition, multiplication, and subtraction, for suppose. So whatever, if I want the addition operation persona should be replaced in that. What does it mean by persona? Let us consider it's a bit stream. Okay. If I want that addition operation, the bit stream should be loaded onto the FPGA. The bit stream related to the addition has to be loaded onto the FPGA. And once that FPGA takes it or reads it, and that addition operation should be performed. And again, if persona B is multiplication, for suppose, if I call as multiplication, the persona B should be replacing it. In the corresponding slide, you can see that. If I want persona A, the persona A will be in that particular bit stream. If I want persona B, that persona B should be there on that bit stream. Means should be in that corresponding, should be programmed in that area. And similarly, if I want persona C, this particular bit stream should be programmed in that corresponding area. So I hope with this you must have got a clear understanding of what does it mean by partial reconfiguration. The partial reconfiguration is the resource utilization will be constant, and whatever the operation we wanted, we can do it. Is that okay? So this is the main idea behind this partial reconfiguration. It's really a very enhanced or a very good technique because you will understand in future slides. Okay, I don't want to get into the technical things as of now. In the next few slides, we will go into that. Okay, so see here we will be using a dedicated resources, a separate resource. As I have already said you, means the area, the room will not change. The area of the room will not change. Okay. Similarly, the area in which this particular bit stream should be programmed will not change. Inside whatever the application or the functionality can change, but the area will not change. This is the main target of the partial reconfiguration. So if I tell you this point, someone will be having a doubt. At that time, I also had a doubt. So the first doubt was, where should I store all these bit streams? How should I, first of all, how should I program these bit streams? Generally, generating a bit stream is a quite easy task. If you have written a perfect RTL, either any of the tools, Vivado or Quartus, will generate as a very good, will generate a bit stream. Where if you can program, you can directly dump it on, by generating the bit stream and programming, you are dumping some code on the FPGA and you can get the result. But when there are multiple bit streams, how can it operate? So we require a method where these bit streams are to be programmed one after the other. Whenever we require an operation, that bit stream has to be programmed. This is the point which you need to remember. Whenever we require some operation, that bit stream needs to be programmed. If that bit stream needs to be programmed at that particular operation, first of all, we need to understand that all these bit streams are to be generated is point number one. The second point is that we should require a higher layer where you should be able to program this bit stream into the FPGA. So these two things, this separate layer or the higher layer which we are discussing, this is known as hardware software co-design. How we can do that means with whatever the available resources. I'm not speaking with respect to the company thing. Sorry, something happened. I'm sorry. I'm really sorry. I think I have touched it something. Fine. So we require a higher layer. We require a higher layer. Sorry. We require a higher layer. That higher layer is called as hardware software co-designs. So I will tell you the idea in a very crisp way. Initially, I will just generate the bit streams for this. And after generating the bit streams, I will store them in some particular, either the SD card or in some SRAM memory inside the FPGA or in some EMIF, the external memory interface inside an FPGA, or we will store in any one of our required methods. Later, whenever I wanted to program it, I will tell from the software that inside the hardware, this needs to be programmed. And the tools, whatever the tools which we are using, either the Vivado or the Quartus will do this for us. They are very intelligent. Whenever you ask them, see, load this bit stream, they will load it for you. But we should follow some rules. We should try to understand. That rules, I'm going to make a discussion today. Okay. So I think, yeah. So first of all, whenever I'm asking you about this, whenever we are making a discussion on this partial reconfiguration, there are several resources and a few are supported by the partial reconfiguration and a few are not supported. For suppose, there will be, we already know that there are some memory blocks, core routing. The routing, core routing is nothing but the routing mechanisms between the multiple logic blocks or the LUTs or CLBs or anything. Okay. So, or inside any DSP blocks or something, all the things. So this routing, memory blocks, DSP blocks and logic blocks. Logic blocks are the main things where the data will be stored. Okay. You can also call them as LUTs, LUTs. Okay. And registers. Registers also will be a part of it. So all these things support the partial reconfiguration. Only two things doesn't support the partial reconfiguration, that is IO blocks. If you are taking an FPGA at the surrounding, at the complete surrounding of an FPGA, you will be having this IO blocks, IOBs. In the Xilinx, we mostly call them as IOBs, input-output blocks or bounded IOs. Okay, at the end of the FPGA, before we will be having those blocks, and also the clock control blocks. How to have a reconfiguration for these two, we will discuss later. First, we will discuss how this reconfiguration method will be there for the logic blocks, DSP, all this, whatever the possible conditions. So first of all, what is the key idea behind this partial reconfiguration? So the first thing you need to remember whenever you wanted to do a partial reconfiguration is, you need to have a clear boundaries. You need to have a clear boundaries. The boundaries or the partitions should not be cross. It should not be a cross boundary. For suppose, let us consider for us module A is one particular functionality and module B is another particular functionality. The relationship between the module A and module B should not be there. If that is there, you cannot do this partial reconfiguration. This is one, it's not a drawback, it's just its functionality. Okay, so you cannot compile without partitions. That's the main rule. You cannot compile without the partitions. So everything should be having a separate logical sections. So for suppose the partition A and the partition B should be separate. You cannot have a cross boundaries between them. So this is the first rule which we need to remember. For suppose, to just state an example, see, I can't keep all the examples in the slides because it will consume more slides. So I will try to pitch up my examples with whatever my experience or something, my understanding. So generally, if you are having an addition operation, the addition operation will be having two inputs and one output. But for suppose, if the addition operation is having three inputs and one output, and if the multiplication operation is having two inputs and one output comes from the addition operation, then this partial reconfiguration is not possible. You need to think of some other way for that. Means partial reconfiguration only with a different idea you need to think of. So there shouldn't be any cross boundaries. That is the first rule to go through this partial reconfiguration. Next. Just a second. Yeah. So next, what are the rules? See, this is one more rule. Okay. So generally, whenever there are two different partitions, you cannot state in such a way that the output of the one partition should be as the input of the second partition. In that stages also, the partial reconfiguration is not possible. To state an example for this, already we made a discussion like whatever our room is there, the dimensions of the room, means the entry exit points of the room should not change. Am I correct? The entry and exit points of the room should not change. There should be only change with respect with the inside of the room. Inside room has to be changed. It can be a dining hall, or it can be a workplace, or it can be a sleeping place, or anything. But there shouldn't be change in the entry and the exit points of the room. Means whenever we make a discussion like this, the doubts will be like, sir, can I have one entry point and another exit point? Yes. Can I have the same entry point as the exit point? Practically, with respect to FPGAs, it's not possible. Okay, but on one particular, whenever it is a washroom, whenever it is an sleeping area, I want one entry and one exit, and whenever it's an work area, I want one entry and one exit. It's not possible. Okay, so that means this particular register IO rule is the same example which I have discussed till now. Okay, the second rule. Okay, so the second rule is that whenever, make sure that no much output should not be there inside this personas or inside the bit streams. Why? What happens? As we already know that if we are having more boundary, means for suppose more outputs are there, obviously if the fan out is there, there is a chance that one or the other place, if the routing or the placement changes, we will not get our required outputs. We will not get our required outputs. So, and also it's too expensive even. Okay. And as you already are aware of this, generally most of the FPGAs means generally they will be like an SOC. Okay. So generally to connect something, an external IP to this corresponding SOC, you require some very good protocol. For suppose AXI, most of the Xilinx things require AXI stream based protocol or AXI Lite a few days. Means if you are working on a very high data, very high speed data, you will be having a stream if you are having a stream of data. And if you are running on some minimal data, you can go for AXI Lite. But if you are really running on memory based kind of a data, you can go for AXI memory mapped. So most of the things nowadays are on either AXI Lite or AXI stream. if you can observe. I'm not generalizing. There may be a few different things, but in some general idea, I'm just telling you. Okay. So whenever you're having more number of outputs, it takes more number of, means the output of the partition should also be more, and automatically it will be very tough for you to run with the timing. At the end of the day, timing needs to be matched. Code, everyone can write it, but the only target is to match your timing, right? That's the very toughest part with the partial reconfiguration. So if there are more outputs, it will be very problematic for us with respect to the time. Okay, so that's the reason why on the right side, on the right hand side, you can see that there is only one output from A to B. Okay, so that will be really helpful for us. And inside that, you can write some logic, and from that, you can generate some other things. That's a different thing, but it's more important that the number of outputs has to be, or the fan out of that particular bit stream has to be limited. Okay, and yes, and one more thing, whatever the inputs and the outputs, as we already discussed, the entry and the exit points should not change. If you can see over there, if there are 3 inputs, you can leave an input unused. For suppose in the multiplication you are having 3 inputs, you can generate a partial reconfiguration IP for an adder with 2 inputs only by leaving unused one other input. But you can't tell that my addition should have 2 inputs and 1 output, and my multiplication should have 2 inputs and 2 outputs. That way we cannot define. Okay. So generally, if you can just check it, here we come with the first technical term with respect to the partial reconfiguration, static region. Static region. So what does it mean by the static region? The static region is nothing but the region which will not change. Or else, for suppose in the starting, before in the initial slides of the partial reconfiguration, before even sending some persona, there was some area which we have highlighted on the FPGA. That region is called as the static region. So this static region has to have a fixed number of inputs and a fixed number of outputs which are common across all the reconfigurable modules. So the second technical term for the day will be the reconfigurable modules, RM. Okay, we will get to know about that in the next slides. Next, has the slide changed? Yeah. So here you can see that in the earlier slide you can see that if I can means the persona 1 uses 1 and 3 and the persona 2 uses all the 3 inputs, means the 2 has been left unused by the persona 2, and here you can see that the 3 has been left unused by the persona 3. But in the static region, whatever our number of inputs are one and the same. That is the thing which I want you to focus. Okay. Now there comes a question. Okay, what is that? Generally, let us consider we have initially programmed an FPGA with an addition module, add, and suddenly you are programming an subtraction module. So already addition module has been programmed using the partial reconfiguration. There will be a partial reconfiguration decoupler which will take care of all these things, and from the software you have tried to program. There will be some time delay. Am I correct? Practically, if you think in a practical VLSI way, there will be some time delay between this addition module and the multiplication module. Means this module, whatever the module, I have to give the input from the software. The software input should reach that corresponding code, and from that code, I want to enable my PR decoupler. I want to tell my PR decoupler that you need to decouple with the previous bit stream, and now you need to load this new bit stream. This new bit stream is somewhere inside this memory, so I need to search that new bit stream. I need to program this FPGA, and later I will get the output of the next bit stream too. What happens between this? What will be the output? That should be the major doubt. Okay, so that's the reason why we use this freeze logic. We use this freeze logic. So this here you can see that there is the output from the PR region is connected, and there is a mux, and to the mux the one output is from the PR region, whatever the dynamic reconfiguration module, and the second input is from the constant value, any constant value which we will be giving, and later we will be taking the freeze control, and later means there will be a signal called as freeze control. All these things will be inbuilt regions actually, and this particular thing, this freeze control logic has to be used in the static region, obviously, because the static region will not change, right? So whenever there is change in the input, means the output of the PR region is changed. If we are making the freeze control to be some particular select line in such a fashion to select the PR output, you will get that same. But if you are selecting the constant value, you will get the constant value. Okay. So this freeze logic or the freeze control plays a major and a crucial role. And it has to be used in the static portion, not on the dynamic, means not in the partial reconfiguration. It has to be used in the SR, static region. But how about the timing? Timing. Obviously, we know that we will be facing more issues with respect to the combo logic. The combinational logic. If at all we are having much of the combinational logic, it's really tough for us to arrange with the timing. Obviously, you require multiple hops. That discussion also will be made by me. Okay, you will be requiring more number of hops, or you need to go for some different methods like multi-cycle paths or something. So if at all, so better if you can register everything. The best idea for us to try to register most of the data. Try to register in the sense just use a register, a D flip-flop or something. So if you can register that, it can really help you in the timing. Am I correct? So to register, and there is an advantage here. There is an advantage here. If you can register, if there is some enable, if you are taking some that same freeze control signal as some enable, if you can register that, if that signal is not enabled, you will get obviously the previous value. There is no need for you to even check it. So the D flip-flop is the same only, right? Only on the passage of the clock, it will change the data. And if on the passage of the clock, if you are taking some enable signal, when there is a passage of the clock and when there is an enable signal only, the data will be changed, or else the data will be as in the previous case only. So usage of a flip-flop instead of this mux will help us in both the ways. One, timing. Two, the combo logic will be reduced. Whenever there are more number of registers, it will be helpful for us in taking multiple hops. Okay, so that's the reason why we go for this type. Is that okay? So this is a very better method. As I have already said you, it's an edge triggering. Whatever the edge trigger, whatever the means, the rule is that whatever the edge triggering you are using on the whole circuit or the whole FPGA, either the NEG edge or the POS edge. Mostly we prefer the POS edge, but in an exceptional cases, in a few circuits as per the specification, we go with the NEG edge. Only in the exceptional cases we prefer the NEG edge. So whatever the edge we have taken, based on that edge, you could be able to change this corresponding value. Okay, so this will really help us. Registering is better than mux because timing is very important. My senior, always when I joined this present company in GRL, he used to tell me, Bharat, anyone can write the Verilog code, but the person who can control the timing is a real FPGA design engineer. If you want to be a real FPGA designer, obviously he was telling like we will be testing your Verilog basics, digital basics, system Verilog basics and everything, and we will take you. But timing, it is not about the basics, it's upon the application. You need to be very dynamic at that time. So that's the reason my senior has said me, he was my manager, my mentor, my guru. He has said me timing is important. That's the reason that word is there. Timing is important. Okay, fine. So I think, yes. So this is the basic idea of what we have been discussing till now. There will be a static region, and whatever our persona or whatever our bit stream, we are going to call it as PR, partial reconfiguration module. So we are having multiple reconfiguration modules and we need to load that particular PR modules into a static place. This is the main target of this partial reconfiguration. Okay. So I thought it would be a very good summary, and that's the reason why I have used this slide. And here it comes. So here, as I have already said you, we need to generate multiple bit streams initially, because we can't tell the FPGA that be dynamic. Obviously, every one of us know that Verilog and everything is a static language. It's not means like C, it's not a dynamic one, it's a static. So you need to tell everything in advance. And based on your inputs, it will work partial. It will work on the reconfiguration phase. So first here, for every partial reconfiguration, we need to generate the bit stream. And that bit stream needs to be loaded. That bit stream needs to be loaded. Whenever I tell that this bit stream needs to be loaded, whenever I tell anyone that this bit stream needs to be loaded, the first doubt which everyone would ask us is, where should I load this, or from where should I store this corresponding bit stream? As I've already said you, storage of this corresponding bit stream can be anywhere. See, here I have taken an example. It's a directly image from the Intel website only. I have given the references at the end. You can see them later. So here this example was shown with respect to either the ARIA 10 or the Stratix 10. But if you come for the latest Agilex also, this will be possible. And if you are coming towards this Xilinx related FPGAs, with the Zinc ZC702 or anything, Kintex, Zinc, everything, it is possible. Except with some older boards, like very starting boards like Basis 3 and all, these are not possible. But wherever you are having a multiple ARM Cortex A9 cores, sorry, wherever you are having a software, means wherever you can load the Xilinx and you can work with the bitstream, sorry, wherever you can load the Linux and wherever you can load that bitstream in that particular dynamically, in all those boards, it's partial reconfiguration is possible. So this image explains us there has been a memory, there is an external host, just it's a CPLD or a CPU, it's different, and we will be having some PR pins, and from that it is connected to the either whatever the board which we are having. So as I already said you, to just crisp on this particular slide, we will be having a memory, where inside that memory we will be storing this data. Either it can be the memory or it can be an SRAM interface or anything, or EMIF, even that can be also possible. But most of the times EMIF, we are not going to use it for the partial reconfiguration. We mostly, for suppose if you are having an SD card, we try to store the data on the SD card, and whenever we want, we can call it. Okay. And I know, as you're all the faculty professionals and all, you will be more oriented towards the proofs. So that's the reason I have even shared you I have done a few examples on my own, and that's the reason I have shared you this particular thing. Here you can see that, sorry, just excuse me a moment. Sorry. Sorry. Yeah, sure. Sorry. Here you can see that I have worked on this ZC702 board, and here all the three are the reconfigurable partitions. The first one is an empty one. The first, if you can see on this particular, I'm just trying to highlight it. Okay, this is the first one, is an empty one, which we are going to call it as a base logic. The second one is the reconfigurable partition one, and as every one of you can observe, it's a 16-bit multiplication. So whenever I'm calling it as a 16-bit multiplication, obviously the result will be, the maximum result will be of 32 bits. So that's the reason I have taken the output as 32 bits. Is that okay? So, and the result is 32 bits. Even though that, and one more thing, if I have taken this AN and BN as 32 bit and 32 bit, I cannot take the result as 32-bit because obviously in the multiplication we require double the size of them. So that's the reason we have only in the reconfigurable partition 1 we have done this. And in the reconfigurable partition 2, you can see that it's an add-on, it's an addition. So generally if I show this slide, obviously I will be receiving, I know that I will be receiving a question like if both of the bits are 32 bits each, obviously the result should be 33 bits. So just as an example, I have taken this just to test and show everyone the simpler example. I have taken this. Okay. So and I have taken the synchronous reset and in that active low synchronous reset. Okay. So this is what I have said you like this is the math PRIP. So what does it mean by the math PR is see there are two reasons. I don't want to hide anything. Actual example in the Xilinx website what they are going to give us or in the right now it's AMD. In the AMD's website contains the same name mathpr_0. When I was trying it I just worked on the same name and later I am habituated to the same name. And if you can see that here there is a Zinc PS, the processing system. Okay, and from the processing system, I already said you right. We require some as it's an SOC. It's an SOC. We require some protocol because whatever we need to write and whatever the SOC needs to get synced. That's the reason we have used this AXI interconnect. The reason for this AXI interconnect is whenever there are multiple AXI modules, this AXI interconnect will be able to communicate better. Okay, and next comes this partial reconfiguration decoupler IP. What does it mean by this PR decoupler? PR decoupler is nothing but whenever you wanted to load some bit stream and that corresponding bit stream needs to be coupled. Okay, so coupling and decoupling of those corresponding bit streams to the PS, to the processing system. As everyone of us know, there will be two things, the processing system, PL and PS. Okay, so whenever I try to communicate a corresponding IP onto the PS, this PR decoupler will play a crucial role in taking which corresponding IP and what are those inputs and how to reconfigure them, all those things, how to decouple the previous bit stream and how to couple the present bit stream, all these things will be taken care by this decoupler IP. And as I have already said you, this mathpr_0 is 1.0, a pre-production IP. Means always whenever in the older versions of the Xilinx we get like this, it's a pre-production and all. Even but nowadays it's been restricted. You cannot see that. Okay. So in this corresponding IP, whenever I'm trying to load some corresponding bit stream, how does that particular bit stream load is in the Zinc PS. I will be telling means from the software. I will be telling this particular Zinc system like, see, I wanted to load this corresponding bit stream and that particular information like the corresponding bit stream needs to be loaded will be sent to the AXI interconnect and directly it will tell that decoupler means the decouple signal is for the same. It's directly connected to the GPIO. So that will inform the PR decoupler that yes, so and so thing is getting happening. So obviously whatever that please try to load this in the math PR place. So the same functionality will be happening with this complete thing. And here I have just taken the AXI timer to just capture the timing. As I've already said you, I wanted that freeze logic, right? So I wanted to just calculate whether the timing is really how much time it will take. In order to calculate that, I wanted an AXI timer, and that's why I have taken AXI timer. AXI timer is not a part of the partial reconfiguration. Just out of my curiosity, I have taken it. And here comes this one. So what is this? Whenever you program something on a Xilinx, in the Vivado software mostly, because in the older versions it's not available. This Vivado software will show you how much area it is occupying. It's they call it with a different name, the sites, the slices, sites or anything, or the banks, anything. So means in Quartus it's a different name and in the Xilinx it's a different name. It will show us in which area your code is getting placed. In which area the code is getting placed. whenever it shows this, obviously here I have selected this much area, telling that all my bit streams have to be programmed in this area. See, actually, as of here, you can see whatever the area which I have utilized is pretty high. As I've said you, I just wanted to show you an example. I don't want any accurate things, because once we are okay with the good thing, we are okay with these things, we can go with a very good examples in a live demo only. It's very easy. So I just taken as an example. That's why I've selected so much of the area. It's very pretty high area for multiplication and addition. This much area will not be consumed, because 32-bit addition, obviously it may consume 32 to 40 registers max, 32 registers, and with some combo logic, some LUTs. And obviously multiplication also, it should be near to that one and the same. But just as an example, that's why I mentioned my example. And finally, if you can see it here, there are three types of files: binary, bit, PRM. Let's not include what are those PRM, because some information related to this partial reconfiguration modules will be stored in this particular PRM modules. We wanted only two things. One are the binary files and the second are the bit files. So whatever I said you, this corresponding, I already said you, like we need to create or generate the bit streams for every method. For suppose addition, I have taken three methods: addition, blanking, multiplication. So for every method, I have taken two bit streams each. One is the full bit string, second is the partial bit string. Okay, so that's the reason why I have used this. So I have generated all the bit streams, and I've copied all these bit streams into the SD card. SD card, because we already know that ZC702 or Zboard contains the SD card interfacing. So I wanted to use this SD card interfacing. And I have directly programmed. Here in the example, you can see that it's asking which operand you want, and at the end it is asking of the choice. And here, whatever on the screen tool which you are seeing is nothing but the SDK, the software development kit of the Xilinx, or the right now AMD Vivado. Okay, so this particular thing will help us in this is nothing but the software part. And in the same image, if you can check it on the left hand side, you can see that there is an SD card.c and SD card.h files where it were used for SD card interfacing, the software interface which we have made it on the hardware. So there will be some couple of coding methods which we need to follow, which will be set by the Xilinx manual only, and a few things we need to assume and we need to try on the trial and error basis. But this one really works. So this is how I tested it. I missed a few images of the results, so that's the reason I was unable to paste the result. But it's really working. It's a working codes actually. So this is about the partial reconfiguration. See, I don't know how much time I have taken on the partial reconfiguration, but I really am in love with partial reconfiguration, because wherever I try, we try to incorporate. There were I can't tell you the scenarios in which I have faced in my company, but we had a couple of places where we were in a dilemma, what to do, when to do, and all. So at that time, we used this partial reconfiguration. So at that time, it was a very good piece of work from the company's side, and we were really happy with whatever the efforts we have kept and the result. Customer was at the end of the day, he was pretty happy. So I love this partial reconfiguration technique, because this on the FPGA, it wowed me. Okay, fine. And coming back, initially I made a discussion that for two different things, you cannot do the partial reconfiguration. One is IOBs, the second is whatever the transceiver configurations or the PLLs. So initially we thought that the partial reconfiguration is not possible. So this slide explains you better about the partial difference between the partial reconfiguration and the dynamic reconfiguration. So the partial reconfiguration is for the core, means the main core logic, and the dynamic reconfiguration is for the periphery. Periphery is nothing but the transceiver configuration. Okay, chalo. what happens on this transceiver configuration? Okay, so generally let us take, how can I tell you an example? Yeah, let us take, let me put up an example of a display port. I cannot mention much, but to up to a normal extent which is available on the outside I can share it. It's not a problem with, it's not a proprietary. On the outside, we have some information about the display port. If you are interested, you can also go through it. It has a fantastic file layer and a link layer. Fantastic, which is very tougher to implement, but easier to operate. That's the DP for us. Okay, fine. Let's not deviate. In the display port, generally, if you can observe, there are multiple speeds. The maximum speed which a display port 1.4a can run is on 8.1 Gbps. Means 8.1 gigabits per second of data should be able to travel, and obviously your clock should be the same. Okay, means whenever I talk about the clock, there will be a quite variations, because as 8.1 Gbps is very tough to implement on the FPGA. So that's the reason why what we try to do is we try to increase the data width. By increasing the data width, we will be reducing the speed, means on the FPGA, but the actual operation of the actual speed will not change. It will be the same. So I'm just speaking on an example basis. So let us take the DP 1.4 takes about 8.1 Gbps or gigabits per second. But means obviously, and whatever the DP 2.1a protocol will take about 20 Gbps is the highest speed. 20 Gbps means 20 gigabits per second. So if you are designing a DP IP, for suppose you are designing, your target is to design a DisplayPort IP. Can you tell your customer that, see, if you want to operate on 1.4a of maximum of 8.1 Gbps, please use this type. You first switch off your system, remove the DP cable, and again place the another DP cable. You remove the DP cable from the monitor. You again place that different DP cable. Can you tell this to your customer? Is that end product will be a successful one? No. We want a 100% accurate product where the customer should not be, here two things should be there. If you talk from the side of the customer, he should be pretty happy. He should have less efforts. If you talk from the side of the user, customer and user both are different. If we are sitting in the place of the user, we don't want any much complexity. As a user, I hate it. I hate complexity. I want a very fantastic and a sophisticated laptop before me. So I can't tell anyone that please remove this cable or insert this cable again. I can't tell them. So if I want the maximum speed of the DP 1.4a of 8.1 Gbps, or if I want the maximum speed of DP 2.1a of 20 Gbps, dynamically, this particular device should change. So generally you can ask me, so Bharadwaj, what is the difference then? Earlier it's working on 8.1, now it's working on 20. It's not that case, no. We will be having so many issues. How can the clock change? How can the clock change dynamically? How can a clock signal change? The clock wizard has to change. The clock signal has to change. With respect to that clock signal, our complete logic which we have built has to change. It's not as easy. So here, the partial reconfiguration cannot be used in this case. The dynamic reconfiguration will help. So I think now you can understand. If someone asks you what's your target with the dynamic reconfiguration, you can easily tell them. If you want to operate on the higher speed of 20 Gbps, and the least speed of DP 1.4a is somewhere around 1.62 Gbps, I think. If I'm not wrong, yes, subject to correction, but I hope 1.62 is correct only. 1.62 Gbps is the least speed, and 20 Gbps is the highest speed, highest frequency or something. So I want a dynamic shift between these things. So here, means our code can change, but how about the hardware on the FPGA? Our code, we can write it dynamically, but this hardware change can also be done from the side of the software, which is pretty interesting. That's the dynamic reconfiguration for us. And here, if you can see that, that's the reason why I have taken this as multiple trans-receiver configurations. Because actually, if you are really aware, trans-receiver, PLL, all these things will be the main inputs in the hardware part. And from that, whatever the clock signal which we are generating, that clock signal will be acting as input to our actual core. Okay. So, but this dynamic reconfiguration is not supported by all the devices. A few devices it supports. For example, you can take in very high devices like ZC102 in the Xilinx or in Agilex 7 series or Agilex F series, which has multiple F tiles. So those type of very high, what we call high-end devices, which can offer you a very good data rate, can only support this dynamic reconfiguration. But it's the most happening. Everyone was shocked with this when this particular paper was out into the market. Even me, I was really shocked. How can someone do this? That was my question in an exclamation. So generally, it's a theoretical side. Whatever I have said you, the same thing should be on this slide, but it's okay. Let's move forward. Yes, earlier I said that the trans receiver and PLL settings are supported by the dynamic reconfiguration. But even though here two things are not supported, IO blocks and clock control blocks. So how to make them support is still running on, and I think in the next few months there is a very good thing which is coming into the market when we can have a very good discussion on that. But as of now, the trans receivers and the PLL settings are really supported by the dynamic reconfiguration. See, this dynamic reconfiguration is really what I can say, it's very internal to every company. They will not reveal those details outside most. And I'm also not supposed to reveal that particular details. So that's the reason this is this is available in the outside environment only. So I requested my company persons, but they were not, they were hesitant because still it hasn't reached the academia yet. So they said, no, Bharat, just if you want, you can take this slide. And that's why I've just taken this simple slide. But even though it's a simple slide, let us understand ourselves better. So here there is an FPLL, fractional PLL, a PLL, the trans receiver native PHY IP, PH5 means the physical layer, because obviously all these things will be placed on the physical electrical layer block. No? So that's the reason why most of these things will be really dependent on the PH5 IP. Before the PH5 electrical block till the PH5 sub block, we can manage it through the coding, but this PH5 block is the actual hardware in which your data is getting transferred. So generally, if you take a clock, if you take the trans receivers, the output will be mostly in the off-chip protocols. In an on-chip, it will be directly in terms of the bit streams or the packets. But in the off-chip protocol, obviously your data will be in terms of some ASK or some keying methods, or in some single bit data transfer only it will be there. Some serial protocol only it will be using. Okay, so obviously that's the usage of the trans receiver. Here it is the trans receiver reconfiguration controller. The above one is a PH5 reset controller. The ISSP in system probes. Okay, and next the QSys system. And in the QSys system, you can see something like external slave interface, JTAG to Avalon master device. Avalon is means most of the Intel devices use this Avalon. From JTAG, they will be converting it into the Avalon, and from the Avalon, it will be directly sending. We will be sending our data to our respective things. Okay, but here what happens? Same as the partial reconfiguration. In the partial reconfiguration, what we have understood. Generally, we need to store some bit streams at some place. When that particular bit streams are configured, when that particular bit stream is called, that bit stream will go and sit inside the FPGA, complete its task, and when we tell that, okay, you come outside, it will come outside. The same thing with the dynamic reconfiguration, but here everything will be in terms of the register configurations. Means inside the register, you will be configuring everything. Everything will be configured inside the registers. To configure these registers, it's not an easy task. We will be running months together just to configure those registers for this corresponding trans receiver reconfiguration. So once that configuration details, which register to configure, what happens if one particular bit changes, will be stored in the ROM. Okay, And when that particular ROM is there, based on that particular ROM data, the reconfiguration controller will reconfigure it. When it reconfigures, it will inform both the transceiver IP and it will inform the QSys system. The QSys, the Quartus system, it's a QSys, we call it as it's a complete package. So it informs the JTAG to the Avalon master bridge and the external slave interfaces. At the same time, when we try to configure this AV transceiver native IP, will try to bring that corresponding data from the FPLL and it will try to load that into the actual PHY layer. And inside this, there will be some rules like what happens if some PHY reset happens or something. So that's why that PHY reset controller will be there. See, I'm not supposed to reveal most of the information than this, but really, I think in the next couple of years, it will be out in the market. At that time, we can actually have a live demo where you will be really shocked. You can connect an CRO and you can see that suddenly you will get the 20 Gbps and suddenly you will get the 1.4 Gbps dynamically in a very faster fashion with very less changes and less jitter. Okay, so this is the partial reconfiguration. Sorry for not sharing more information about this. Sorry, the dynamic. Sorry for not sharing the more information because it's not out into the market. Okay, I hope you can Google it or you can just search for the ChatGPT or anything. It gives some information which is right and some which is really wrong. So that's the reason I haven't included all those images. ChatGPT was giving more images, but a few are wrong. And it's not happens in that way. Okay, fine. I think till now, what we have discussed, I wanted to dynamically load my FPGA. How to do that? If you want to dynamically load a transceiver configuration, it should be a dynamic reconfiguration. If you want to dynamically load the actual only the core idea, it's a partial reconfiguration. But whatever I'm going to discuss next is the game changer in the complete industry. How? For suppose, so to explain this, whenever I was reading about this in my initial years, when I joined this company, initially I was given this task of understanding this architecture and how can we implement to our existing architectures. That was the task which was given to us. And we have moved very closely with those corresponding teams, the actual designer teams also, we have closely moved with them. And at that time, something struck me like the example. Means obviously while reading anything, we require an example. So the example which struck me was, let us open a Google map. In this Google map, if for suppose the Google map is telling us to move towards the right, but suddenly we have moved towards the left. Google map is telling us to move towards the right and suddenly we have moved towards the left. What will happen? Obviously, the Google map in some fraction of seconds or else in some fraction of in a minute, in less than a minute, it will change the direction and it will show us the map by changing its architecture or changing the direction in which we need to go. It will directly tell us that, okay, you have taken a wrong route, no problem. I will show you an alternate route. Okay, the same inside the FPGA. The same inside the FPGA. But why? Why do we require this inside the FPGA? That's the question. Is my example okay? I don't know, I can ask you or not. Can I ask you this? Is my example okay? So don't mind me with my example. I try to correlate everything with the practical or else I can't remember much. So my examples will be like this. I will try to find out the examples from every step because it means initial days I was not like that, but once I entered the research field, I became like that. Okay. So suddenly you can ask me like, Bharat, you are telling this much. Why will in a circuit or in an FPGA, the dynamic course action will be required? Means, so that's what I'm going to explain you today. This one. This is a conventional FPGA architecture. See, I have taken the example of the Agilex because it's very good. Means Agilex is showing very good examples. So that's why I have taken, but it's means it's mostly this hyper retiming is actually first of all started with Intel boards only. Means nowadays it's Altera. Altera means because Intel and Altera are separated now because means they are under the same company but different entities. So here we know that we will be having the row interconnects and the column interconnects, and we will be having multiple ALMs. Let us consider multiple modules. Logic as logic blocks LBs, and whatever the beside one is nothing but the registers. The combination of logic and the register is called as ALM. ALM is nothing but the adaptive register module. So the Agilex contains this, and this ALM with respect to every device is different. Okay, so whenever I'm considering this, if you can see that this is what an ALM contains. An ALM contains an adaptive LUT. Adaptive LUT in the sense if you are programming it for 4 inputs, it will be 4 input LUT. If you are programming it for, yes, someone? Any doubts or something? Okay, please, please, sir and ma'am, if I'm running short by the time, please let me know. I will try to complete faster. Okay. So the adaptive LUT is nothing but it can adapt itself automatically. Means if it is a 4 input, it can work for, it will work with respect as a 4 input LUT and all. And how to do that and all, it's a proprietary of the Intel. Inside it's a very good logic behind also, but we can't discuss it. And here we will be having 4 registers per ALM, 2 full adders, and multiple mux, multiple selection configurations and all. This is what an ALM, the adaptive logic module, contains. So if you can see that this is how the clock routing happens inside the Agilex devices. But why am I telling about this clock routing is, means it's not much important, but to understand the next concept, this is important. Means the clock routing will be in such a fashion that it will be a 32-bit, means there will be multiple clock tap multipliers, and there will be different row clocks, clock switch multipliers and all. So here, for suppose, if I want to connect the ALM which is on the bottom left to the top right ALM, obviously there are more routes. If you can see, I can follow any route. I can either follow any route. Okay, but see the amount of the interconnect which we have used. The amount of the interconnect which we have used is nothing but the wire only. Whatever the wire is there, it's nothing but the delay only, right? Rho L by A. So because of that resistance, there will be some delay. So obviously, here there will be quite a delay. Means let us consider from one register to another, from one ALM to another ALM, whenever I'm traveling through a longest path, it takes some more time. The time will be high. Tau is equals to RC. So when the time is high, obviously the delay between these two things will be high. Whenever the delay between these two things are high, automatically means here there may be a setup violation. It will be mostly a setup violation. Okay. So in order not to do so, what is the solution? It's a conventional logic. I can follow any path. Even if I follow any path, if the length, if I'm placing one of my ALM here and one of my ALM there, if I'm directly, if there is some requirement for me to place, if they are not the synchronizer registers, right? If they are synchronizer registers, you will tell the tool that you need to place them beside only. But here you can't tell it. There was some of your functionality where you need to place that there and this here. So automatically there is a long route over there. Because of the long route, there is much delay. Because of this delay, what will happen? The setup violation may occur. So obviously, this is the solution we go for. And just as an example, I'm showing you pipeline. Add a pipeline. It really helps. Okay. So what will you do? First, you will code in this way. After coding after all the placement routing on the FPG, it can be dynamic, but you can also route it on your wish. So once you route it and after all the code and all, you will get a timing error. That the setup time is violated and I can't generate a bit stream. That's the tool will shout at us. And the tool shouts that, obviously you will think like, okay, tool, I know what's your problem. You are unable to match the timing between these two ALMs and I have added a pipeline. But But see, by adding a pipeline, has the problem been solved? No, the problem is not solved. Why? Because the problem number one is every time the tool throws an error or shouts at us only, you will be able to identify this, or else you cannot identify. Second, once the tool throws an error, you need to go through the complete path, in which path it is going and what is happening and which path is throwing an error. So you need to first analyze what is the combo logic, what is the combinational delay there, what is the combo delay there, and what is the register delay there, what is the timing over there, means whatever the T, what is the wire delay over there. All these things you need to compute. What is the, means all these delays you need to compute, and you need to come to a plan that, okay, see, let me use a pipelining because I can't change my timing. The overall clock time period, I can't change it. So that's how you will get, but it's really a problematic situation because it's means obviously, and here one more time is nothing but earlier in one hop I was able to get the data in one clock. Okay, but here I require 2 clock cycles. That is third problem. 3 problems we are having. So that's the reason. Obviously, considering that ALM delay or lab delay, everything it's a problem. Okay, so it's a disadvantage. So how we create a module where it will automatically check for its timing, automatically check that, okay, here I'm violating this. Whatever the user who has given the code is violating the timing. Okay, let me do one thing. Instead of in this way, let me go in this way. The tool computes it dynamically. How will that method will be? That method is called as the hyper. So here this is an example of an bypassable hyper register. It's just like nothing but say if you want a signal to be delayed and sent, or if you want a direct signal to be sent, you can send it. It's a mux, it's a selection logic. If you want to select the delayed version or if you want to select the present version, you can send it as your wish. So we call it as bypassable hyper registers. So what is the idea which at that time Altair or Intel people came out is, they came with an idea like they have filled all these places with an hyper registers. All these places with an hyper register. So you can ask me, Bharadwaj, what is the advantage of it? Here all the orange things will show you the hyper registers. So the Intel people came out with an idea like all these registers will be very dynamic in routing. And one more thing, you can also observe that here at the inputs, at the ALM inputs, I don't know if you can see my cursor moving or not. At the ALM inputs, you can see that the inputs are normal. But here, if you can see that even at the inputs, they have used the hyper registers. So what is the advantage of this? So generally, if I go in this way, here, if I am having this particular interconnection, the tool will automatically calculate everything. And because every path is registered, it will choose whether to take the registered output or it will choose whether to take the direct output from the mux. It will compute the timing internally. It will come out with a very better timing methods, and it will automatically come out with a better timing. Okay. See, now let me consider it's the same path, but automatically the tool is also considering that instead of going in that path, I can go in this way. Okay. And finally, the advantage of this particular method is, from our side, from the user perspective, the hard work will be reduced. The tool will take its problem. The tool will be having internally, it will be running so much of the processing things. So that's why all this higher Agilex means whatever the quarters and all, they cannot run on very lower systems. They need very good systems because the internal computations which are done by the tool will be pretty high. So the tool will automatically calculate that, see, this is the best path and this is where I'm not able to miss, means in this particular timing path I can go there. So if I cannot go in that timing path, I will also the tool will also suggest the user that, see, with whatever the hyper registers also we are unable to take this path. Please check this path. Please try to add a pipeline register in this path. All these things the tool will tell us. So from the side of the user, you can happily start your simulation. You can sit aside, relax, have a mug of coffee, and by the time the mug of coffee completes, the tool will tell you some things. So that's how dynamic it can be. So this architecture where we are using interconnects using the hyper registers is called as hyperflex architecture. And it's a very advantageous method because in the earlier ways we were just having only the LUT delay, and means the local routing delay was too much. Here either we can skip the local routing delay whenever we wanted dynamically, and it can be considered by the tool. But everything comes with a problem. Every solution always will be always having a problem. As a researchers, I don't need to tell you, because as a active researchers, all of you, you should be having, you have more knowledge on that than me. So obviously hyperflex architecture is an advantage, but there is a problem. The problem is these are the rules you need to use. What are those rules? You should avoid using the asynchronous resets or avoid using the synchronous clears. Okay, either it should be directly a synchronous reset directly. That's it. And that too, mostly that also you need to avoid it mostly. And if at all that is there also, you should not use wildcards in the timing constraints. That is throwing an error. You should directly, means as every one of you know, whenever we are writing the timing constraints, if you use the star, it means that whatever all the arrays, if you are declaring it as some n-bit register, for suppose of 7 down to 0, if you want to time according to all the registers, we will be using a star over there in the timing, but that is not allowed. Do not use any preserve registers, and clock enables cannot be used. If you are following this corresponding rules, obviously you are ready to use the hyperflex architecture. And what is the advantage of this? Means I schedule like it's a hyperflex. Okay. And what is the advantage of this? For suppose in the first image, if you can, I think I'm left with 8 more minutes. Please, I will end my session. It's I find it interesting here. Please, in 5 minutes, I will try to end it. Okay. So in the first image, you can see that the inputs to the LUTs are registered, and directly from the LUT there is a combo logic. Again, the LUT is there, and from that again we are using two. Again, we are registering it with 2 flops. Obviously, the tool will consider that. See, if at all there is an means if you are using like that, we cannot match the timing. So let me do the backward retiming. So what it will do? It will place this corresponding registers. It will place this corresponding registers. It will place this corresponding registers before the LUT. So that with this the timing is satisfied here. With this the timing will be surely satisfied here. So this will be automatically done by the tool without any user intervention. Or for suppose if you are doing in this way, we call this as forward retiming. If you are using 2 flops before the input and the 2 LUTs are directly connected, obviously it will think like, okay, again the timing may be a problem because 2 LUTs connected together will be a the combination logic will be too high. And there are more chances of missing the setup. After the setup time only we can go to the input. So obviously we will miss it after the setup time or something. So that's the reason why here we can go with the forward retime. Is that okay? And one more advantage is there. For suppose if you are taking 2 LUTs here, earlier what we were doing is, instead of, if for suppose these 2 LUTs or the combinational logic is too high, you also must be knowing it. If the combinational logic is too high and we are unable to reduce the combinational logic into the parts and we are unable to register the combinational logic, we were using the method of multi-cycle paths. Because you are just instructing the tool like, see, I can't complete this operation in 1 cycle. It may require 2 cycles or it may require 3 cycles. So please do not consider before this. This is what you are instructing the tool in the multi-cycle operation. So with the help of this hyper retiming, you will be able to understand or remove this multi-cycle exception. See, I haven't posted images for this. There were wonderful images in the spec, but it comes with an very IP. It's an IP for that company, so I haven't posted it. I'm sorry. So this is the idea of the hyper pipeline. What does it mean by the hyper pipelining? Is if you are, instead of directly coding it, you can use some hyperpipes in between. Automatically, the tool will defaultly consider. See, for suppose in the first logic, if you can see the first logic, directly you have taken 3 flip-flops with much of the combo logic in between. Means logic cloud is nothing but, let us consider it's a combinational logic or an LUT. So here you are using 3 pipelines and you are using a logic cloud, and here you are not using any pipeline. So if you are using a hyper pipelining or hyper architecture, the tool will automatically consider that. See, here 3 delays are waste of time. I can't match the time. Here I can easily match the timing, but here I can't match the timing. So the tool will automatically place this in this way. That is the advantage of, even as a user, we cannot get that much very great ideas. So that's the advantage of the hyper pipeline. So that's why it's the hyper retiming. And see, there are some rules for it. Automatically, whenever our effort reduces, the computer or the compiler effort increases. It takes much time in the sense comparatively lesser time only, but it requires some much optimization or operation inside. So obviously it takes much time, but it's okay because our effort is reduced. At the end of the day, that's our target. So with the help of this different methods which I have discussed, I think these are very new in the market. Still, there are so many things in the market. Where are we using this? Generally, it's an AI. Whenever we take an AI, we will be always hearing to the 2 words: train, inference. For suppose, if you want to train a system, for suppose if there is an if a picture has been captured and if you want to train that system, like if it is a crow, if it is a sparrow, means you need to differentiate them. So obviously you first need to train your system. The second is, whenever you take a picture, it will show you an output like, okay, that's the inference. So for training and the inference, these are the 2 different methods which we are going to use in the implementation of any AI. That things can be implemented on the FPGAs by using this. Even you can train with the help of the FPGAs, and even you can inference, you can get the output with the help of the FPGAs. So IISc Bangalore is doing a phenomenal work on this. Even nowadays, IIT Bombay and every IIT in India, mostly they are working. If you see the senior professors' papers, most of the papers are there on the AI with respect to FPGA. And in most of the things, these are the basics which we need to understand. Okay, so, okay, fine. Thank you from my side. And it's now open for the questions. I think we are having 2 more minutes. It's open for the questions. Anyone? Was it okay? Was the presentation okay? So if you are done for the day, I mean, if you are done for, yeah.
Yeah, participants, if you have anything to ask, you can ask. For clarifications, you can ask questions.
Okay, if you have nothing, I just wanted to conclude with some words. See, generally, I think every one of us are aware of this. Yeah, you are audible. I think you are Amaya, ma'am. Yeah,
Yes,
please.
yes. Currently, I am taking that ASIC subject which we have in BTech Electronics and Computer Science, where there is system Verilog. So, which type of mini projects or practicals should we give to the students so that they can have a more opportunities further, because they have selected VLSI track for their future? And in VLSI track, we have this ASIC subject, SOC subject, and analog VLSI.
I'm not aware of this analog VLSI because analog VLSI is completely related to the implementation. ASIC. ASIC. See, the very good projects which even though if for us also, if some resume comes to the picture, the first thing we will be seeing is the very good projects like you can implement a very good encoders. 8-bit NB encoder is one of a very good encoder. 128B, 132B is a very good encoder, which is actually used in the practical PHY layers, scramblers, or as I have already said you, all the DC communication techniques will be there, right? Whatever this Manchester encoding, those will be in the output of the PHY electrical layer. So you can ask a student to write down a Verilog code with respect to this Manchester encoding. Mostly in this off-chip protocols, Manchester type of encoding will be used mostly. So you can ask them to write that, or you can ask them to develop an RISC-V coprocessor. And you can ask the students to buy some basis 3, means with respect to FPGA, you can ask them to buy some basis 3 boards, because directly with respect to the ASIC, you require the actual tools, or you can go for some open source tools. With respect to FPGA, the tools are free for limited time.
Okay.
So that's the reason we mostly suggest the students with Vivado. Most of the students messages on LinkedIn.
We have Vivado, we have Boolean board, Zinc board also.
Yeah, that's very great. If you are having a Zinc board, you can ask a student to implement a RISC-V minimal processor, and you can ask them to add a partial reconfiguration to that. That will be really good work. Or you can ask a student to implement a discrete wavelet transform, or means like lifting based or convolutional based, and you can ask the student to implement on that FPGA board, and you can ask the student to divide an image into the parts in the MATLAB and generate the same image by connecting to the VGA port of that Zinc board. The student can gain lots of knowledge from that, I think, ma'am.
Yes. We have cadence also. Because
yeah, that's too great. In the cadence, you can go with the SOC encounter. No, SOC encounter was earlier, but you can have the very good power optimization values and all. Okay, so fine.
Yes.
I think I have answered your question. Good afternoon.
Madam. I'm Dr. Umman Taragan.
Nice
Professor and Dean
presentation.
of Bassalius Christian College, Kerala.
Yeah, sir. Please, sir.
My question is that your concept of reconfiguration is very good. However, I would like to know whether for space application where failure is not an option, can this concept be deployed since weight is a concern for us? I was earlier
No. So in the means as of now, this is not implemented in any space applications because still the research is going on. If you can really observe, sir, that particular freeze control and all, at that time there will be a minor delay, and in the space you can't have that delay. Your circuit should be 100% reliable.
And also the radiation also we have to take into consideration.
Yeah, by taking everything, still as of now it's not in the application with respect to the space, sir. As per my knowledge on the we are using a few things without our knowledge with the partial reconfiguration, but in the space I think it takes some time.
The advantage what I was looking for is that the weight can be reduced because same thing can be reconfigured for many applications. That's why.
Yeah, actually for that the research is going on, sir. But see, I think in the next couple of years you can find it. And also if you can reduce that wait time between these two things, means if that freeze logic or something where the error rate can be reduced, the BER is reduced, you can have a very good, you can use it in an accurate space applications.
Okay, thank you. Very nice of you.
Yeah, thank you, sir. Thanks a lot. Yes, anyone please? Someone were trying to talk, please. I'm sorry, I was talking with sir. So please, anyone? Yeah, someone, I was unable to hear you, please. It's Anusha. Yeah, please, ma'am. Ma'am, Anusha, ma'am, please. Okay, so if not anyone, okay, fine. So thank you all the professors and professors. Really, it's very nice of you to interact with all you people. You're really a very great, means you're really making strong the next generation of our country. So I'm really proud. I was an assistant professor. So with all your degrees and all, I'm really proud of you, and I'm taking this opportunity as very great for myself presenting before all of you. Really thank everyone. But if I have made some minor mistakes in the slides or some non-technical words inside, I'm really sorry. But I hope you liked my presentation, and if you want to contact me, my details will be there with the organizers. My LinkedIn profile also will be having the same name, Bharadwaja Pisupati. You can contact me even on the LinkedIn. I will be surely helpful for anything which the students can require. As a student and as a researcher, ex-researcher, and as a person with respect to the industry, I want more students to come into this. So I'm really happy to share my whatever I know with any one of you at any time. Thank you. Thanks a lot. If you're having any doubts, you can approach me or else we can wind up the session. I think we have crossed the time by 5 minutes. I'm sorry.
Thank you, sir. Thank you for the wonderful
Thank
session.
you. Thank you.
The
Thank you.
clarity and the depth you brought to the subject is really amazing, sir. Thank you.
Thank you. Thanks a lot. Thanks a lot. So if you're not having anything, I can disperse. I think the next guest would be waiting.
Yes, sir. Yes.
Thank you, sir.
Yeah. Fine. Thank you. Thanks a lot. Thanks a lot. Thank you.
So, dear participants, we have rather packed schedule today, so we request your kind cooperation as we move quickly to the next session. And now the time has come for a final academic session of this FDP. It was always said that the last note of a song lingers the longest, and I'm sure today's concluding talk will do just that. We are honored to have with us the eminent speaker Dr. Dayala Kumar, sir. Dr. Dayala Kumar is an innovative hardware architect with expertise in high-speed VLSI and FPGA design, specializing in packet classification, DSP architectures, and system prototyping. He holds a PhD in electronics from IIITDM Kanchipuram and MDES in MDES in experience. He has worked as a project scientist at FIST, senior project associate at UCAL, and the lab engineer at IIITDM under SMDP C2SD. He is the founder and CEO of Mr. Gen Technologies Private Limited, incubated at IIT Madras Pravartak, focusing on non-invasive geophysical systems for sewage and septage management. His contributions include FPGA-based low-power transceivers, non-repetition watermarking engines, and fabricated designs in Skywater 130 nanometer PDK through Affable's MPW shuttles. A passionate researcher, he has published in ACM journals, presented at international conferences, and guided projects on IoT, smart systems, and sustainable technologies. Sir, it's a privilege to have you with us today. And now the platform is yours, sir.
Yeah, thank you, ma'am. Am I audible?
Yes, sir.
Yeah, thank you, ma'am. Thank you for giving a nice intro to me. So,
Thank you.
yeah, let me share my screen. Is my presentation visible?
Yes, sir.
Yeah, thank you. Thank you for the confirmation. Okay, so today I am going to discuss about the open source EDA tools and their relation with the AI, artificial intelligence. So previously, whatever the closed source tools or whatever we discussed, everything doesn't have the AI support, but slowly they started adopting it. So the open source EDA tools are started revolutioning, and the advancement also it's keep on improving. So once anything start uh, getting advancement, the opportunities and also along with that the challenge, the positive and negative, both together will start grow. So that's what I'm going to discuss today. So before starting, actually, ma'am already said I am founder and CEO of Maestri Technologies, also Desai Technologies. So the Maestri Technologies, it's especially concentrating on the geophysical investigation. So we concentrated on three different products on it. One is underground sewer and septic management line. Second one is a border security force, underground tunnel detection. Third one is a concrete quality check. So all are related to a geophysical investigation methodology. The second one is a Desai Technologies, which we concentrate about the customized software and hardware solution. Especially we concentrate for the smart IoT applications along with AI processor. So we started developing our own AI processor with that. So both the companies attached with HVR CSE lab to play DM Kanjipuram. So before starting, I need to discuss what is this VLSI and what it can do. So whenever we say about this VLSI, we always say about some kind of chip fabrication or some kind of FPGAs. That's what. But it's not just a chip or IC fabrication or FPGA, but it is the actual heart or soul of the modern era. So the advancement happened both in the hardware and software side. Whenever we say about what this era, we always talk about the digital era. So this digital era has two simultaneous growth, one in the hardware side, another one in the software side. So the software grows very fast and it requires very high speed computational power, high speed data transfer power. But the problem here, whenever the software start growing, whenever it demand high speed architectures in any of the application, then the hardware has to meet. Otherwise the algorithm will start developed, but it will never be utilized. So we have many algorithms like that. The algorithm already proven theoretically, but still it is not under use in the real time cases. So the VLSI can do beyond our imagination. So we can say that whatever the chips, this is millions and billions of transistors inside it, and that many kind of switching it's happening per second. So we say that now gigahertz processor. So we proudly say that 10 to the power 9 or 10 to the power 12 operations per second. But thing is that that many different switching around that billions of transistors has to happen parallelly. So that's what actually we are expecting. So whenever these many transactions happen, how we are going to manage? Previously, we never care about how these functions will happen and how we are going to design all these things. But the problem here, it's changed. So we are actually designing a soul and heart of the modern era. So the soul and heart of the modern era, it's not just started very recently. The timeline is very far away. So we know that zero is a actual base, the digital era or the digital part. Whenever we discuss, that is binary, zeros and ones. So this digital part started with zero. So the first recorded zero, it started at 3rd BC, the first recorded zero in Mesopotamian civilization. So that is recorded but nowhere used properly. So after that 500 AD, Aryabhatta, he started giving a proper meaning for zero and how to use it effectively. So that started a first revolution and changed the complete mathematical thinking in a other dimension. Then why I try to explain this timeline, this is related to the modern era and related to the AI part. So whatever we are talking, it may present for the future or may have a different name or it may change. So whatever happened, that is based on the previous history. So that history makes a path to give the proper revolution, to give the proper modernization. So if the 3rd BC or the 500 AD event not happen, then the remaining haven't events completely changed. So everything has a reason which is connected earlier. We have a one thought. We everyone using a number system as a decimal. As a human, we are using a decimal number system, and we habituated. We closely connected with decimal number system. But if you look on it, the machines, it's we are giving a binary. So since the binary is recorded or given a proper meaning at 500 AD, we never use the binary number system for the machines. So everything has a reason. But why we adopted binary number system? Why not the other decimal, hexadecimal, octal? These many number systems are evolved, but all these number systems, even though present, and out of which one number system as a decimal has upper hand with the human civilization, still we try to force the machine to use a binary instead of others. That is not because binary is easy for the computer, because we designed it. So even far as binary, it's very difficult to understand in a direct way. We need a encoding and decoding methodology to understand it. So here, if you look on it, the timeline actually says the reason. So at 782, 850, we created algebra. So the algebra trying to talk about the mathematical function. So how we have to understand the actual or real world application in a mathematical way, that too in a calculative format. So we define the variable, we define the equations, we try to solve the unknown functionality using the known parameter. So, and then binary, it evolved at 1679. So if you look on it, why binary all evolved? And since binary evolved, binary arithmetic. So since decimal is there, algebra came. Binary is there, that binary algebraic function. That's what we call it as a Boolean algebra. Similarly, octal function evolved at 1716, 1854. Again, the Boolean algebraic function, Boole. And then hexadecimal started evolving. But the thing is that all these hexadecimal, octal, all are present far before our thinking, because all these number systems evolved based on the availability. The availability is nothing but the human hands. So since we have a 10 fingers, decimal number systems are there. But what about the other number system? Even the number system has a reason about our hand only. If we know that whenever we try to calculate the number of days in a month, we used our hand. We try to count based on the humps and bumps between the fingers. So if you try to count it, it will be 1, 2, 3. The total 12 possible cases will be there. The gaps alone, if you try to count it. And similarly, the cuts in the finger, if you try to calculate, it will be either 16. If you leave the top one, it will be around 12. So the humans started counting based on the mark present in their hand. So some of them started following the octal, some of them started octal in the sense the gaps. So some of them started following the Chinese number system, 12 symbol number system, that is the cut without the top lead of every finger. And some of them started following the 16 decimal, which is hexadecimal, which is all the cuts in the finger. So some of them started following the decimal number system, which is all our finger. So, but how binary started evolve? Binary is not because of the reason of the human hand, but because of the human invention. So, thing what happened? 1 second. Around the 1600 somewhere, the electricity is found out. So this create a application of that means electricity. It's not just evolved only with the bulb along with the switch. So the switch is a first input hardware element and bulb is a first output hardware element. So in the switch we have only two state, on and off. That's what binary actually evolved. So the binary number system, the reason is the first availability of the hardware. So since the hardware available, the humans started thinking about why can't we create a hardware which understands the binary number system. So that's what the Boolean algebraic functions, everything started about. So at last 1873 set theory, Venn diagram, and all these things helped to improve the logical based thinking in a better way. Previously, whatever the algebraic function or whatever we talk, this is purely a mathematical based thinking. But the set theory and Venn diagram create a next dimension to think about and think in terms of a logical way. So this create an additional option. Why can't we create a logical operations, the switching functions? That's what the vacuum tube, flip flops, and gate, all these things happen. So the first digital computer around 1941, but still now around 2025, we have a supercomputer, everything. But if you look on the OS and flip flop ICs and digital radio, all are trying to help us in a better way to improve our timeline. But just I want to show something. The first timeline, whatever I have shown, third BC, 500 AD, 780 AD. So the time gap is very far. So even after the binary also, if you look on it, 1873 and 1880, 1886, it was around a decade. So around here. But after this first digital radio, 1969, if you look on it, the timelines for the improvement started shrinking. So 1971, 70s to 80s, if you look on it, 72, 80, 81, 85, 99, every 5 years once or every 3 years once, the improvement started developing, which means the communication started increasing. So they started spreading the knowledge in a faster way. So not only with the communication method, similarly, the machine started helping us to think in a different dimension. Previously, only with the human thoughts and only with the human behavior, we started developing everything. But here, the actual modern era started. So the digital era started with FPGA. So previously the ICs, whatever we talk about, this is a specific functionality. But the problem, if you want to create a particular IC, the cost will be very huge because initially we need to create a IC floor plan, and then we need to convert those IC into IC plan into a GDS file. Then we have to go for a testing, verification, and then fab. After fab, again testing, verification. In case if the IC start failing, again we have to refabricate. But the cost and timeline, if you look on it, it will be very huge. To make a single IC from scratch till the complete testing, it will take around a year if it is an experienced team. So the reason they start creating the function and they'll iterate it multiple times with the simulation, and then they'll create a GDS, then they'll go for a fabrication. The fab team will take minimum of 6 to 7 months, including the silicon wafer till the die preparation. So after that, again the IC once come back, another 6 months they has to test it. So the complete 1 year, whatever the cost it incurred, also it's very huge. So they are tired of all these things. They started creating another IC which can emulate the function. That's what the FPGA came into picture. So any kind of digital functionalities are there. Why can't we program it? Why can't we change the functionality of the hardware and we'll deploy it in the real field, and then we'll test what is happening in the real field? Because the IC, after it fabricate in the lab environment, it will work. But what happens if it goes to the real field? It will fail. Many of the cases it will fail. In some of the cases it succeed. So why it is failing? What are the other parameters we left out, we didn't consider during a fab or during a design? So that's what the team need a explanation. So what they did, they tried to develop a FPGAs for emulation, but the FPGA actually gives an additional option. It's not just for emulation. It replaced many of the application with the hardware, space applications, radar applications, uh, underwater applications, even for the consumer electronics. So many of the places it replaced much of the functionality. Still, FPGAs have a upper hand in a other way, because when we talk about the processor or a specific functionality, there are some positives and negatives. The processor actually it's a generic functionality which depends on the ISA architecture, and billions of instruction has to run to complete a single functionality. If a specific functionality, we can't change it, the specific IC, ASIC IC, we can't change it for any other application. That is fixed for a particular application. In case if that application requires an additional improvement or additional parameter change, then we have to throw the IC and we have to fabricate it again. So these are the problems. So but the FPGA, it will not depends on the IC. We can create any kind of functionality, but the only thing, it will work for the low clock frequency. That means maximum of 1 GHz. So 100 megahertz to 1 GHz. This was the frequency range of the FPGA. But thing is that this is not based on the instruction. So if you want to complete a single functionality with the processor, or it need billions of clock cycle, but the same thing can be done with a single clock cycle. But still, there is a limitation. How much hardware utilization I have to go, and whether the hardware availability satisfies the functional requirement. So these are the major drawbacks of the FPGA. But still, the timeline, if you look on it again, 80, the first FPGA, 90, and then Ultra came with the second. Then 2000, the SOC came. This SOC and PSOC changed the it created another dimension. Something like previously we created ICs for a specific function and we tried to embed in a single executional board. But later they thought, why can't we create a single IC which can have all the functionality inside it itself? So much of the interfacing and the power loss we can avoid it in the board. And the size also get reduced. So this what actually we thought. Then the PSSoC actually changed to the next dimension, 3D ICs. So now the Xilinx and Ultra, they named into something. The Intel, the AMD bought a Xilinx and Intel bought Ultra, and they started started developing a processor along with the FPGA. So now the SoC have an upper hand. Now at 2020 started the AAML. So the AML also nothing new. Previously it was a probabilistic theory, then the fuzzy logic, and then sometimes it was approximate computing, and then MLA. So the name, even if it change, the functionality behind it, it's same, but with the additional features. So these additional features, whenever it come, the old name and the old functionality alone not satisfies. So it have a new name on it. So in the future, we may not know whether the A or ML word may present or may not present, and something else, in the sense some other name will come in terms of A and ML. So, but whatever the thing, the basic availability is same. So this is the actual basic. I just gone very fast till that because many of you knows about it. So I started with the EDA, the electronic design analysis tools. Actually, what is this area? Everybody knows. So some tools are there which will help us to create a simulation or the RTL or GDS2 files. So we can able to create a virtual hardware elements, and we can able to simulate or we can able to convert into an hardware functionality, which can be either fabricated as a IC or which can be deployed as a hardware function in the FPGAs. So that's what this EDA functionality helps. But this is not just, as I said, just a basic tools or the circuit design tools, but this is the only platform for us for the creation of machine's core control. So why I said this core control, in the sense the machine's body, whatever we talk about, this is not just mechanical. At present, it's the robotics and electronic parts. So all these things has a major control it. So previously we talk about the machine can replace a human, but now many places it replace, but still it can't override human, because however the machine improved, this parallelly humans also started improving ourselves. So that is the reason we are trying to give more and more knowledge to the machine. So until unless we didn't understand anything properly, we can't give those knowledge to a particular machine. So whenever we try to give a additional dimension, additional feature, additional knowledge to a particular machine, then the machine need have a capability to adapt it, capability to operate it, capability to function it. So if they want to do all these things, then the actual core control, the body of the machine should have the upper hand. So if the AI algorithm or the ML algorithm or ML model expects to process a particular function in a fraction of second, in a microsecond or millisecond or second, even seconds, the hardware should have the capability to operate it. Otherwise, many of the real-time applications will not be feasible at all. The automated self-driving vehicle, the rockets, aeroplanes, and right now we are doing many of the medical surgery through online with robotics. So all these functions, they are real-time. So the machine has to take a decision. The machine has to process the inputs within a fraction of second. Even a microsecond or a nanosecond matters here. So that much level of computational power it has to give. So it's not only the computational power. What about the size? So what about the speed? So all these things. So the speed, power, areas. Generally, they'll call it as a PPA, power and sorry, power, delay, and area. So this create a more importance on the chip. So the importance is what, in the sense it try to enables the chip design. So the EDA try to enables the chip design and try to make a better verification, so that the synthesis, placement, and routing, everything will be proper. But thing is that the EDA tools also keep on improving. So initially, whatever the EDA tools given, that is based on the basic set of rules, and then whenever we felt some particular rules, it's actually a mechanical step, something like the steps has to be repeated again and again without knowing the end result also, which means we are trying to optimize. The tool can optimize it, but manually we have to repeat it. So when we try to repeat all these steps with a few parameter change logically, then the chip design, it's trying to improve by itself. But what actually it's trying to do, it's actually trying to control the data path and control path. That means the functionality of the data path and control path. That's what it's trying to control it. So the the synthesize, placement, and routing, all these things trying to control how the body has to be created. The synthesize actually it's trying to choose the mathematical functionality of the RTL code or the EDA part, whatever we develop, the simulation part, and check whether the functional is properly present. And for this particular function, what is the actual hardware available during a fab time. So that's what the synthesis will do. The placement will do all once it selected all the library cells, try to place it in a different place, and it will try to connect all these cells based on the functional requirement. So, but all these things happen manually in the initial time. Later, the tool understands it need not to be initial. We can create an algorithm and we can automate it. So this automation happen in a certain logical way till a certain period. So later, after AI and ML start evolving, they thought why it can be a logical, because for some kind of application, some kind of requirement, it can be logically fit for that particular function. But if we change it, it will optimize still further. But how can we change? How can we bring the optimization? How can we make the closure very faster with a lower effect? So all these automation can be done with the AI integration. But this who will create this AI integration? We need to create a rules. So what are the rules? So and these rules should be well defined and formulated. So previously we don't have the rules, and we don't we didn't define the rules in a proper way. We didn't formulate it. But now all these are completed earlier. So that is possible, which is AI in EDA is possible. So the closed source tools, you are aware of it, Cadence, Synapsys, Mentor Graphics. If it is a programmable device, AMD Xilinx, Intel Ultra, and Microsemi. They are the major competitors in the market, academic or industry side. So if you look on all these tools, it is almost $50K to $500K per year. This is what the cost of the tool when we are trying to use it. But the problem here, to create a single IC only for the tool alone, if we try to spend this much, what about the manpower? And what about the verification cost? What about the testing cost? And how much time period we have to spend? How many manpower we have to spend? After all these things, when we create a GDS or the end file, how we'll fabricate? What about the fabrication cost? So after fabrication, what about the testing? So the overall cost will be very huge. So if you check out all these things. So this tool cost alone, it's almost 10 to 20% net. So for the entire time period. So they want to reduce this. So open source community or open source community started evolving their own tools. So for the IC design, if you look on it, OpenLane, OpenRoad, OpenSTA, OpenRAM uses Magic, IEDA or IEDA. So these are the different tools for the IC design. So in this OpenLane is a wrapper. It doesn't have a own tool, but it has a all open source tools inside it, and how effectively we can use with a better ML and AI agent. So the OpenLane and OpenRoad has a already incorporated its own ML and AI agent for optimizing the synthesis part and optimizing the routing part. So what actually it will do based on our constraint, it'll try to optimize the placement, it'll try to optimize the synthesis flow, and it'll try to iterate the flow in a multiple run and try to give the proper or not proper. It I can say it's a approximately proper. So how effectively we can give, that's what it will think. So even the closed source tools didn't give these options to their customer. They started developing it. But the open source tools initially started because already the open source community knows what is the actual requirement, what is the pain point. So they started developing based on the requirement. Already the closed source tools are present with some kind of functionality, but still it has a pain point to iterate or pain point to do it something. Yes. Anybody want to ask anything? Okay. So similarly, the programmable device, OpenFPGA is there, or few XML tools are there. So similarly, the languages are Verilog, System Verilog, VHDL, and BlueSpec. It's finally developed by IIT Madras, Indian made with IIT Madras team. So using a BlueSpec, they created their first processor, so Shakti processor. The Shakti processor complete code developed with BlueSpec. And the RTL compiler, open source RTL compiler, iVerilog GTK. Other than the closed source platform, we are talking about the open source tools. So what is the strength and what is the limitation? So the strength of the open source tool will be it's completely transparent. So everyone knows about the source code. So what are the different bugs it can create, we can easily understand. And it can be customizable since the source code is available, completely transparent and no license cost. So we can customize it based on our need. So that is the strength. But the problem here, the limitations, the PPA gap. So the power per area. So how much power we have to produce to access on the chip. So already the closed source tools are well versed to optimize all these parameters. But the open source tools can create a basic, a smaller chip, smaller functions, it's fine. But when we go for larger and larger, so the complex chips. So that is the major problem. That is the gap between the commercial and open source tool, and that is a major limitation of the open source tool. So how can we solve these things? So few things can be solved with the AI and ML part, few things can be solved with the open source community and their effort. So if you look on it, there are different foundries in VLSI. So everybody knows the TSMC library, Samsung, and UMC library, SMIC library, and global foundries. But all these are paid libraries. So all these libraries are nothing but to fabricate a IC, we have a machine. In that machine, what kind of machine setting I have to give to create a particular IC functionality. So for that, what they developed, they created a foundry library. So the library has a settings target file. So if you create a code, so this code has to convert into a particular logic cell. So if I want to choose that particular logic cell, and if I want to place the logic cell in a particular area, and if I want to route it with the different nets, so what are the different machine settings I have to give? That's what they created. So the TSMC created their own library, TSMC library, Samsung they have that one. So it was mentioned as 5, but at present the 2 nanometer it's going on. Already the 2 nanometer fabrication it's started. So when I talk about this 2 nanometer, I need to talk about something else called dark silicon and failure of Moore's law. So everybody knows the Moore's law expects every 18 months the number of ICs in a square area should double. But the problem here, when whenever it double, actually it's trying to reduce the area or the number of atoms per transistor. So which means if a per atom per transistor, whenever it reach below that, we can't able to reduce. So which means after that the number of transistors can't get doubled after 18 months. So that's what the failure of Moore's law will say. But the thing is that I'm not talking about only with the semiconductor. I'm talking about any kind of material you choose for the transistor, but one atom per transistor. That time it will definitely fail. So they're checking additional options. What are the alternate things? So that's what the foundries are thinking about. But the same way in the open source community, they are very far away from the closed because we are talking about 2 nanometer in the closed source. But if you check on the open source community, they are literally far away, 120 nanometers, 65 nanometers. These are the nanometers still they are working. So the standard cell libraries readily available for fabrications are Skywater nanometer and Skywater 120 nanometer and Free PDK. Both are 120 and 65 nanometer technology. So these two foundries giving a library file for the open source community. But the thing is that again, their nanometer is very far. Okay. So what are the different functions? Again, so the nanometer scale fabrication, that is a first function in VLSI. So this nanometer has to change to pico or something else, whatever. But the problem here, whenever we talk about the VLSI, previously it was only a IC, but right now it was a system on chip. So this is a system on a single chip SoC. But what happens after AI incorporation? Whether it is a system on a single chip or a machine on a chip. So we don't know, but that is the actual future enhancement we are looking on it. And one more, right now, if you look on the entire EDA flow, there is a semi-custom flow, there is a full custom flow. Similarly, there is an analog flow, there is a digital flow. In middle, there is a AMS, analog mixed signal processing. So few portion of the ICs process the analog signal, few portion of the ICs process the digital signal, which means we have to create few portion with the analog signal processing end, few portion with the digital signal processing end. So few portion with the semi-custom flow, few portion with the full custom flow. So few portion of the IC is created with the transistor-based model, and few portions will be created based on the RTL-based model. So this heterogeneous integration. So not only with the analog and digital, there is a chance in future a photonic IC may evolve. So the photonic based signals also can able to process it. Already a three-dimensional integration came into picture. The next one will be advanced packaging. So the IC packaging. Once we create a IC, we need to package the IC so that it can be used in a multiple environment. So what kind of packaging technologies we can go for it, and the low power design techniques. So this actually our major work in our team, because we are whatever the application we are working, which is in the nanometer and the nanoampere and picoampere range. So the signal whatever we are processing, they are very small signal, and it can be deviated even with the tap or walking or nearby electronic device usage. So we need a proper signal conditioning circuit and a low power design technique so that the signal processing will be in a proper way. So this is the major change in the VLSI domain. So automation and verification already we talk about it, but what about memory technology? No one talk about your memory. Over talks, they'll talk about your IC design, semi-custom, full custom, and even the FPGA part. But what happens to the memory? So the memory designing is completely different. So no one talks. Even the IC design, semi-custom, full custom, all are evolved in the last years. But the memory design, it's not much evolved, but still evolved. We know that initially we used a magnetic tape hard disk, then SSD. So similarly, the floppy SSD, whatever we are using, the memory technology improving, but it's not improving in a same scale or same speed of the other technologies. So it is still improving it. But one major change with the memory is now we can able to represent a hexadecimal number system inside a memory. So previously the hardware, as I said, the switch happened because of that we started evaluating all the machines with binary. Then we started creating all the machines with binary number system. So now we have every electronic or digital era devices with a binary number system. But till the hardware not evolve for the other number system, but the quantum and photonics and this memory technology change the phase, so they can able to represent a different number system. Quantum actually started with the nibble. Right now they are targeting for the hexadecimal, and memory already came for the hexadecimal number system, so they can able to store a 16 different states in a single memory cell. So it's not just zeros and ones, 16 different possible states with a single memory cell. So the technology improved in a memory also. This photonics integration, as I said. But is it sufficient? Definitely not. Because initially our wealth defined based on what is available, commodity come commodity. Then they defined the money, so a gold kind of thing. Later that changed into a paper, money. So now all our wealth will be based on the data. So whenever I say about all this digital part, all our data is already stored. Once the data stored in a memory, it is highly difficult to completely remove the data. So somehow we can able to retrieve the data. That even that technology started improving. Even you format, even you delete, even you broke the device, still if the hardware available, there is a to recover the data in a certain range, certain level. So the data, if it is available, it's not only recover, I can read. So that's what the cloud security, network security, everything talks about. The security and trustworthy design. So from the hardware, how we cannot tamper. So there are hardwares now available. So reversible logic, security based hardwares, all are available. So encoded hardware, encrypted hardware, all are right now available, and they are mainly using it. So this advancement uh, can be done with low cost, definitely not, because India right now 1.26 trillion dollar they have invested only for this EDA and VLSI designs. So the miniaturization of transistor density, how small we can do the lithography, how we can able to create a 3D chip. So the new materials beyond silicon, that's what I said. After one atom or 1 nanometer or whatever, the other option. So the new neuromorphic computing. And this alone not sufficient. All these works, if I want to do with only humans and the available technology, it is very difficult. So accelerate it. So specific functionality. So the AI and ML part. So machine learning integration. So all these things matters. So what actually the EDA community expects. So the tool should get advanced so that the workload will get reduced, timeline get reduced. So this workload and timeline get reduced in the sense the total cost for IC fabrication will reduce drastically, because for the 1 year manpower, how much we spend for the 1 year, the tool cost, how much we spent, the 1 year machinery, how much we spend, maintenance, how much we spend, everything will be inside the IC cost one. So if we drastically reduce all these things within a fraction of second or few hours, then the cost also will decrease. So that's what we call VLSI in beyond. So the integration of A and ML, the acceleration given by A and ML. But what kind of acceleration it can give? So if it gives the below whatever the application we have said, the edge computing and IoT devices will improve their features and performance. The 5G and 6G technology already we know that we have a 5G but not effectively. But still we know that some other countries already they went for 6G. Some countries they went for 7G also. The thing is that the hardware should compromise need. If it is 5G or 6G, that much data actually we are sending it. So already the 5G expects beyond the link speed. Already whatever the OC 3192 fiber is there, whatever it can able to deliver the maximum speed beyond it, 3 times more than that, the 6G and 7G expects. So the material has to improve, the medium has to improve. So how can we satisfy all these things? So the background hardware should satisfy. Then only whatever the data rate it's coming, that I can able to process. So the 5G and 6G wireless connectivity, the quantum computing. So whenever we go for quantum, the quantum bits and the other number systems will change the thing. So biomedical electronics, autonomous security and trustworthy auto, environmental monitoring. So the environmental monitoring previously it doesn't have much effort, but right now it is there because the climatic change. So all these things uh, beyond our expectation. So all these areas they expect a very high speed computational hardware. So whether these can be done with the VLSI, definitely it can be, but whether it can be done with the open source community, open source hardware and collaboration, possible, but with a condition. What is the condition again? That we have to discuss why AI for EDA. Without AI also, EDA can sustain. So, but why we are actually adding the need, the actual application need, the demand increased. So if you want to satisfy this need and demand, we need to give all these applications in a faster or shorter timeline. So if you want to give everything in a shorter timeline, either we have to increase the manpower or we need to develop the IC in certain way so that there is no fault. So if we want to create all these things, we need to analyze more and more. So we need to automate the scripts. We need to automate the parameter tuning. We need to accelerate the design space exploration. And we need to assist the engineers in a better way. And we need to predict what can be the timing, area, and power before the complete GDS or complete layout part. So this hardware, this kind of functionality may end with this particular range of area, this particular range of timing. So all these things is a hard spot actually. So how we can able to target these hard spots? So that actually defined with the help of AI. So that is actually giving a bridge. So for the expertise of human and new designers with the machine need. That's what actually we also expect. So whether whatever we spoke, it's happening in the world, yes, actually. So these are the different key projects in the open source community. So the MCP 4EDA, they are actually LLMs architecture. So they are a actual machine learning architecture which helps to improve the PPA from RTL to GDS flow. So this RTL to GDS flow, it's maximum for the semi-custom flow. So the LLM in the sense, instead of creating a code and changing it, so the LLMs actually understand the functional logic with different form, different language. Sometimes we can able to create a hardware using a C, C++, Python, Java also, but in a certain level. So this LLM orchestra helps to create a RTL to GDS. Similar way, the other language, BlueSpec, it's a Python-based compiler actually. So other than Verilog, VLS, sorry, Verilog system, Verilog and VHDL, there is another new languages can be developed or already existing other language because a certain application, certain ML model may be available, the code are readily available in C has to be converted or imported to other language. In case if I want to create a hardware, again I have to convert that and have to create a proper logical function to create a hardware. But these kind of LLMs help to directly use these kind of codes to create hardware, but in a certain level. These are not completely developed, but they started it. Similarly, the IIC pilot. This is multi-agent backend flow. This is completely a AI agent flow only for the error handling part. So the design space exploration and error handling thing. So this is a complete automated flow to check where are the errors and how to handle these errors because few errors are logical based one, few errors are tool based one, few errors are coding based one. So these can be eliminated in a easier. So how to define all these things? So these cases can be checked during the verification process, but the verification will take a much longer time. So this IIC pilot, the I2C pilot actually helps to reduce this time. So the OR assistant, it's a conversational help for the open road. Open road, it's purely for the placement and routing. So the open road actually has the additional duty to place the ICs in a different possible combinations and find which is a better possible combination. So, and it gave almost 80 to 90% of the accuracy to place in a better way. So the OR assistant is a another dimension for the placement and routing. So the 4GDA, it's for the data set. Whatever the AI or ML, when we say, these are not just logic. They are something like a human thoughts. So what we learned based on our experience, based on our knowledge, we are trying to rethink it. So similarly, if the machine also has to rethink, we need to create a data set, the knowledge. So this 4GDA is especially for the data set creation. So the AI EDA model training. So how to train the EDA tools with a different data set. That's what the 4GDA is. So the open road and IDA, it's an open source backend. Actually, it's not open road, open lane. So open lane and IEDA, this is for the core backend services. So they are the complete automated flow from RTL to GDS. So the open lane has both semi-custom and full custom achievements so far. So closed source is there, open source is there. Closed source already occupied the market completely. We know it. So they have achieved a lot. They have developed the ICs. Maximum of the ICs which we are seeing and using in real time, everything is based on the closed source. But whether the open source community achieved anything, exactly, it's achieved. So they have already achieved this automation script for the LLMs. So these LLMs already started adapting by the closed source communities also. Similarly, the conversational assistant for flow learning. So even this is improved and they started up using it. Similarly, the timing closure. So the timing closure is a major important one in the VLSI, that too especially for the IC data. So the open source community already shown 15 to 30% timing closure in a very shorter time span compared to the closed source community. But the last one, dataset creation. So the community to create a dataset, to train the dataset with the actual ML model. So these are the achievements till now the open source community. But whether they stopped here, definitely not. They started developing the ICs with the open source community. So with the AI and ML model. So I'm proud to say that I have completed and I have fabricated 3 ICs with the open source community with Skywater 120 nanometer technology with the eFabless team. So that other than the 3 IC, we submitted 28 ICs for fabrication. So out of which all 28 accepted, but 8 ICs accepted for fabrication. But the bad thing due to fund and other limitation, it got stopped. But whether it is completely gone, definitely not. What are the different A and ML models in ADA used? Something previously, whenever we talk about all these things, a certain A or ML models are helpful. But now keep on the models getting improved. So if I want to go for any LLMs, so script generation and over assistant, always this LLMs will help. So if you want to go for any placement routing, parameter tuning, so the PPA improvement, reinforcement learning is a better option, RL. So if you want to generate a netlist, if you want to represent a circuit, something like I want to create uh, lift mechanism. So for that, I need to create a specific IC. So I don't know the language, but I know what is the logical function. So still I can able to say about my logical function, what kind of netlist, what kind of circuit representation. So this kind of prediction. So it can generate it. So the graph neural networks. So it can generate a graph kind of thing, state machine kind of algorithm, and then it can able to trying to predict and try to create a netlist and circuit background of it. So this kind of predictive algorithms help us. If you want, then GNN will be a better option. So the transformers, this is only for the sequence modeling. So sequence modeling in the sense while creating a code or while go for a synthesis and optimization. So some kind of uh, predefined steps are involved. Then we can use these kind of algorithms. So the supervised and regression model, this is again the PPA prediction only, timing power area closure. From early design stage, the timing area power will not care about it. But the problem, whenever the design get improved, then this timing closure, power requirement area, because whenever we say about timing, will not care about the power much time because the high speed is always power consuming. So when we go for IoT or low power devices, they are time consuming. So how to balance the time and power? And one more problem is there. If the IC size keep on increase, whenever we say about the SOC, the functionality keep on increase, the size of the die will increase, size of the IC will increase. So when I increase the size of the IC, the dark silicon matters. So the dark silicon in the sense portion of the IC will never get a for energy itself because every metal will hold a energy per square centimeter. So beyond that energy, I can't able to push more energy on the metal, but it will start heating it. So what actually it will do? It will not send. It will not get enough power through the IC. So there are different methodology to avoid it. So from early stage to the actual stage, how we can go for it. So the supervised model will be helpful to check all these things because it's a prediction based thing. Last one is a generative model. So this what actually the right now the present community are looking on it. So the circuit placement layout generation. So this is from the NLP, natural language or LLM or whatever. So I need to generate a circuit, I need to place it, I need to create a layout. Everything should be automated. It should be generated from the direct input instead of a coding or instead of design. But whether all whatever I said, these are the advancements. That is fine. But what are the challenges we face? Because the challenges are not simple. For saying I can able to adapt the AI model, I can able to create a ML model, or I can able to create a data set and train. But it's correct. But the thing is that whether it will suit as per the EDA requirement, the production grade PPA gap, The production grade BPA cap in a sense, we know that in lab environment, whatever the circuit we are working, it may work. But when we create a same circuit for the actual environment, definitely it will fail in multiple cases because the production grade expects multiple things. So whether we consider all these things, so the AI or ML part, whatever we talk about, it should consider all this production. So certainly the limited knowledge or limited AI support for the AMS, analog and mixed signal processing. So the digital signal RTL to GDS is better because it's purely a coding. The coding already we given a mathematical model. We proven the mathematical model in the simulation. But when we go for analog or mixed signal analysis, the major problem, the proper mathematical flow is not defined. So it is purely based on the material formation and material property. So how the electron flow will happen, background of it. That's what this analog and mixed signal analysis will do. So the AI support on top of it is very challenging and it is limited resource availability and insufficient open data set. Already I said few communities they started developing a data set, which means data set already not available. They started developing it. So whatever the data set is developed, it's based on the open source community and the quantum of the data set is very less. So the insufficient data set create multiple errors, multiple corner issues can be predicted, can't be processed properly. So the layouts, parasitics effect, all these things can't be handled proper way. So the next one will be scaling to a larger chips. So as smaller chip means there will be very less problem inside it. But if it is larger chip, then the problem happens. So how to solve this case? That is another issue. So that scaling is another problem. Next one, process dependent design. Something like if I want a process dependent design in the sense based on the environment, based on the process, we try to change the design methodology. So what are the different rules we have to create? These rules are not fully captured, so not fully formulated. So who will formulate all these things? Again, that is a limited resource. So these are the first major challenge. Whether this challenge complete here? Definitely not. The challenge still improving. That is the data availability. Few open or large or process mode specific data sets alone is available. Remaining are not available. Either we have to create or we have to achieve it. So the A model or ML model, even if it developed, it can't be trained in a proper way. Second one, generalization. So generalization in the sense already some data is available, but it is not formulated. Who will formulate it? Who will train it? A one tech or one process definitely don't transfer the complete knowledge. So that one proper generalization methodology will not be there. Today, whatever we generalize in the future, tomorrow it may not be available, or it completely changed, or it can contradict also. Today we may say this rule is a compulsory to satisfy certain need, but tomorrow we may say that this rule creates a problem. So we can't generalize it in a proper way. Next one will be a scalability. So training on a large SOCs. As I said, memory is a major bottleneck, memory and runtime bottlenecks. So this is another challenge, but slowly the challenge started reducing something like explainability. So the designers need why a parameter or placement is chosen because whenever A or ML model it says I gave a better optimized design and I gave a better optimal choose of the library component, but why it is chosen that? Why it gave this particular thing as a best? What is the reason behind? We don't know. So later, what will happen? We'll started blindly believing it, even though it is worst. We don't know whether it is worst or not. That's what the present AI bots. So many times, students and others they started developing their code using this AI bot. They started developing their assignments using this AI bot. But whatever it gave, it may not be relevant to the actual problem statement which we asked. But still, students are not ready to read in many times and they started believing this is what actually I need. The same gap will start expanding it. So this explainability is another issue. Integration. So the AI output, whatever it gives, that should be properly formulated as per the EDA tool commands. So whenever the EDA tool command improved or whenever the AI algorithm improved, both should realign and both should share the knowledge how to integrate to the proper command line. The ultimate problem will be AMS, analog and mixed signal gap. So AI is still and completely weak for the custom layouts and verification of the AMS, analog and mixed signal. So I'm not saying about the other normal, full or semi for the larger or smaller, but if it is a AMS, still the AI is completely weak, even if can satisfy for the other difference. So the data availability and quality. So this is another problem which we need to talk seriously. So the lack of large or diverse open data set. So these data sets doesn't has a complete information of the RTL layouts, timing, and parasitics. These has a limited information about it. So this will not create give the proper quality design. So the foundry rules, whenever it get updated, the PDKs are often proprietary. That means the closed source PDKs, TSMC, Samsung, and UCM, whatever we talk about, all are proprietary based. So what about the open source PDKs? Whether these rules, if it change, what the A and ML model will do. So whether it has to update or whether it has to forget the previous. So all these things are not formulated properly. So without a good data, definitely ML models can't generalize anything in a better way. So still a weak and custom layouts designs will be generated using a AML. So this is a major problem. So the generalization and transferability. As I said, if you want to convert that 130 nanometer into 7 nanometer, it is, we can say that it is not that much because it is the same circuit. So I have a inverter circuit which is in 130 nanometer. I want to create a same in the 7 nanometer. We may think it's exactly same, but in the background it's not. So the models are trained per process, per node, may fail for the other. So it's difficult to difficult to adapt across the technology or between the multiple technologies. So because 7 nanometer has additional rules, additional conditions, EMI effects, antenna effects, and since it's very close, the parasitic effect, the RLC effect, everything will change. So the training of A or ML model per technology will never suit for the other. So if you want to suit it for the other, again, it has to be generalized between the foundries, between the RTL libraries. So, so we need to transfer the knowledge not only between the nodes, mean the technology nodes, also between the digital, analog, mixed signal domains. So these kind of knowledge, the transfer of learning between all these models is very limited because a person who's working on analog may have a knowledge about digital or mixed signal, but not completely. Similarly, the others. So even for the machines and the models also in the same way, the reason the data sets availability, scalability and sorry, scalability and complexity. Uh, if I want to say about the scalability in the sense, previously whatever the processor we create, that is started with the 8-bit processor, 16, 32, 64 right now, it's going for but when we go for the large SOCs, not only processor, network processor on top, and voice processor on top, and accelerators on top. So the huge computational memory, the huge computational power, everything when we try to add one on top, then the actual problem occurs. So here the total die size, the total SOC size is very huge, and they has to process more rules on top. So the training or testing for the ML models are very limited, and it is very complex. And one more thing, if you want to run all these things, it should take a longer runtime because the placement and routing, if for the 10 different basic cells or some library cells, if I want to place in an area, then I should have a 10 factorial combinations in a different way, at least 2 power 10. So what about if that number of cells are billions? Then it should be 2 power that billion or that billion factorial combinations in a better way. So that many possible combinations I have to keep, and that many after placing that many combinations, again routing the same routing net from one node to other node can be drawn in a multiple ways. So the AI actually, or AI, the ML actually has a feedback uh, which should slow down the placement on routing. So what actually it will try to do, it will try to take a shortest path or min-max algorithm, and from that it will try to say that based on the algorithm which I have used, it is giving this much area or this much placement possibility, which is far better than the actual, the conventional one. So the thing is that, as I discussed before, it doesn't has a proper reasoning why it is in a particular way, so that it gave a better routing and other things. So the complexity it's still increased. So at last, if I want to integrate a AI into a tool chain, then the problem here it's trying to slowing down the flows because the tool chain expects initially the RTL will be here, then it has to go for a synthesis, then it has to go for the placement, and then routing, and then GDS generation. So this is actually the tool chain flow. But what happens during a synthesis if I want to reiterate it? So it will run for the complete, even open lane. It'll if you go for the one command run flow, it will run for the complete. And then during synthesize, while checking the synthesize report, if I want to change something, again I'll go for the complete. But still they have option to run synthesize alone in a multiple time. But thing is that it's trying to slow down. Instead of speeding up them, it is trying to slow down. Because why I'm saying slow down in the sense, when you run it manually and check few things in a proper way, it's fine. But every time when you are running, it has to run the complete flow and then it will give the end result. So till the checkpoint, at least it has to run. So that is actually trying to slowing down instead of speeding up. And the trust. So this is actually related to the security point. So why I said in terms of security point in the sense, the designer, whenever we think, even now there are multiple talks, a country is not ready to buy, purchase ICs or others from other countries. So they want to make it in-house. So the own country's product. But everybody has some trust issues. So if you want to create all, satisfy all these things, even the AI model which we create or the ML model which we available, it also may create a bug. So the designers need to understand why that AI made a decision and is that decision is trustworthy, whether it can be explainable. Okay, but the thing is that it cannot. It, as per the designer's view, it is just a black box model. So inside the black box model, what is there? What it can do? Everything is highly unpredictable. So the critical chip informations may leak or may not leak, or it can be hacked, or we don't know. So this lack of explainability from the AI limits the adoption, which means many are not ready to adapt because of this problem. So these are the major problems present in the open source community or major problem present in the AI and ML. But whether it is not present in the closed source, no. Even there, it's others too. So they are also say there, but everybody are signing it. Somebody taken a responsibility. If it something happen, I'll take the responsibility. But in the open source or AI and ML, the responsibility is not taken by anybody because the responsibility is given to the user. I gave something for your use. You can use it. So once you use, you can just take a responsibility of it. So that's what they are thinking. So is it possible to integrate all this AI and ML or this open source thing with the existing tools? Actually, yes. The AI outputs can, or whatever the open source community they develop, these are just the scripts or constraints or the layout rules which can be mapped or must be mapped cleanly into the tools. So open road uses all these tools can be adapted with the existing or with the closed source tools or any other open source community also. So this can be done. So the AI suggestions still require a manual correction, which means always the A, if I say it has 99.99% accuracy, still there is 0.01% error. So that 0.01% error has to be pointed out or corrected by the manual method. So the AI, even if it has a 10% accuracy or 90% accuracy or whatever may be, still it need a manual correction in a certain way so that it can able to properly work. We can't blindly say something and say to the ARMM model and expects everything will be packed and given to a complete solution. The solution has to be rechecked, manually corrected in every level. So that's what actually the integration will expect. So the tool ecosystems not fully developed or not fully ready to accept as a AI ready. So this has a provision to accept it, but not fully. So till certain level, it can accept. So the major issue what I talk about is analog and mixed signal gap. So most AI EDA tools focus is only on digital design. They'll say as a RTL to GDS. So this RTL to GDS is talk about the digital or semi-custom flow university case. But the analog, RF, and mixed signal layouts are far more geometric sensitive. So, but these are less standardized. So the AI and ML model need more and more data sets, more and more corner cases, more and more classes to define. Then only these can be formulated. Even with the manual creation, it is very difficult to standardize all these things. That is a major problem with the AMS tools. So the AI tools for analogs are limited. It's not because of the tools or the development, it's because of the data. So especially the validated data. So who will validate and give the data? These can be used as a proper result. What about the community and resource constraint? So openly, if you want to say the community or resources in open source community is not limited, but the limit is in some other way, funding and commercial EDA giants. So the commercial EDA giants, they can market and they can easily adapt the customers in a better way. And already these commercial giants occupied the complete market. So they spend a crores and crores of dollars to use this closed source community, commercial giants. But suddenly, if I want to shift from them, whatever the investment we have done before, everything will be lost. So at least to get that investment in a return, till that time they are forced to use it. So they can't jump directly to the open source. They can slowly adapt, but the problem still they are the open source communities are completely limited in funding. So why I'm saying this point, there is another story, there is another one team which uh, lose many of the opportunity because of funding. So the large computational infrastructure, something like if I want to fabricate a high speed hardwares, the computational infrastructure and the AI model, everything is very huge. But for the open source community, this is limited. They can afford all these things. And third, for the closed source community, the community is working daily and closely. They are solving all the issues. But here in the open source community, it's based on the community interest. They are developing slowly and fragmented, also distributed, which means they were spreaded throughout the world in multiple players. Based on their interest, they'll choose a portion of the EDO tool and they'll try to improve that portion of the tool. So like that, each portion will start developing by one. But This fragmented development actually slows down the complete integration, because think about the complete tool, only a portion of the tool started in developing, remaining all with the same level with the previous versions. So that complete integration will not be effective. What are the different research opportunities? Still, it has a research opportunity, because when I talk about to the institute or else the industry, the advancement, it's not only the availability. So whenever a research option is there, then we can say there is still an advancement is present. So the research opportunities are highly available in open source area, because to create a open and multi-model data set, this is a first major requirement. Then the hybrid approach, half portion will be AI, portion will be heuristic search. So it will be faster and reliable. And early stage predictor, which means before calculating the complete thing, in the initial level, in the RTL level itself, or the timing closure level itself, if we can able to predict much of the congestions in the timing or clock or power or area placement, whatever. So the early stage predictors will try to reduce the time span and uh, reduce the failure rate in a faster way. So next one major problem will be explainability. So since the AI or the EDA, it can't explain why it has done in a proper thing, but still we can able to develop this explainability. So this interpretable results, if it can be developed, if it can be given to the engineers, then they're ready to accept this AI results. So next one will be cross domain learning. So the transfer of knowledge across the nodes. So different nanometer, different analog, mixel, RF. So whatever the transfer of knowledge. Similarly for the EDA designers, EDA tool designers, EDA developers, and EDA usage persons. So all these person has to transfer their knowledge to adapt in every places at parallelly, so that it can be used in effective. So this is a story actually I talk about it. So there is a community, many of you may know eFabless. So this team actually, it's a crowdsourced hardware development team. So this team especially, they try to adapt the open source tool, and they created a foundry with Kaiwater 130 nanometer technology, and they created an open shuttle with the help of Google. Google funded it initially, and they completed 12 open source shuttle. Every shuttle they developed a 50 different designs around the world. So throughout this 12 shuttle, they have made the open source tool to develop in a faster way within 1.5 years. So the fund, whatever available, previously the open source community actually present and they are developing the tool, but it is not widely used. No fabrication happened. Tool development is very slow, but because of this team and because of their step, many of them want to fabricate their own chip. So even I fabricated 3 chips on it. So many of you wanted developing their own chips, students, researchers, startups, even multiple companies, and some of them with collaborate. So they want to fabricate their own semiconductor ideas. So they gave an option here. So you can apply for the chip, and with that idea, they'll fabricate and give you around 200 ICs per design. So I got around 600 plus 50. So 50 is a test IC, and 600 ICs I got the silicon package. So without packaging, they'll give a pure raw silicon fabricated ICs. So we need to test. Hello, 1 second. Okay. Oh, sorry for the interruption. So they want to bring out this open source community, open source tool throughout the world with the open source development itself, so that much of the cost will get reduced. They founded at 2014. Founders are Mohammed Hazim and Sharif Ed and Jack Hugs. Headquarters at CA. But the problem, still it is operational as a private company. Partners and customers are present. Foundries are present. Okay, but still supported by many of the open source community students, and they want the custom chips present, but still they face a challenge. Suddenly Google stopped funding the eFabless, and the capital whatever they have done till now, it is far sorry, too high. So the foundry cost, margins, everything is high, so they can't recur the fund again. The engineering cost, the stress in the finance side, everything is bad. So the market competition also more. The problem here, once the funding stopped, they didn't completely fail. It slowed down their process. So the 1.5 year, whatever they have completed, after that 2 year over, the 2 year it was in the same position. They didn't increase much. So again, it started slowing down. So they can't afford to compete in the market. So they can't scale. They can't increase their volume into multiple designs. So they created a multiple thought. The open source tool can be used in a multiple ways. But the thing is that the challenge. So the tool chain maturity gets stopped. The foundry still dependent on the external fab, and user still not ready to adapt because of the criticality. So this is the actual problem with the open source community. So the open source community, if it want to develop, either the community has to help or everybody has to ready to accept. But the in VLSI, at same time ready to accept, it's very difficult. That's a major problem. So slowly they can adapt, but it will have more time. So okay, I have few time, so I'll just go it fast. So the jobs: VLSI design engineer, verification engineer, physical design engineer, embedded system engineer, test engineer, and product validation engineer. These are the different job options available. So if you complete the VLSI, it is not just front end and back end. These are the different options. Other than that, so we have some more job options. So in the full custom, semi custom, or programmable flow. So if you look on the job role, as I said, AMS, verification, layout, ASIC front end, ASIC verification, physical design, DFT, application engineer, EDA tool, Fab, FPGA, front end, IP, and library developer, physical design. So the indigenous processor, Shakti by IIT Madras, Vega by CDAC, SCL Semiconductors, and then eFabless. eFabless zero processor. Many IITians and some individual person they fabricated. So the three ICs whichever I fabricated, that is a 32-bit processor, a 32-bit SoC processor. So the opportunities slowly started. It's available still with the eFabless and other communities. So these are the challenges: miniaturization, complexity, cost, emerging, and workforce skill gap. So the future AI powered design tools. So once the AI powered design tools are completely ready, then we can able to think the chip design in a better and faster way. So the quantum computing and more than more. That's what more than more. It's nothing but whenever the more get failed. So what it can be. So we can create additional logic on top of more, still to satisfy the law. So alternate number system. Already I said few are already moved to other number systems. 16 or the quantum computing or photonics are the memory based technology, and DNA computing and the novel data representation. Other than the existing number system, we can able to represent some kind of encoded or encrypted data directly. So I'm open to question now. I think it's almost time. Any questions?
Any questions from the participant side?
Shruti ma'am.
Yes, ma'am.
Hi, I'm Amaya Pete. As we have to give the feedback on AICT portal, but I don't know. I was trying to log in. Invalid access. It is giving. I tried to change the password also on portal.
Madam, just a moment. If you have any questions regarding the session, first we'll sort it out and then we'll get back to the topic.
Okay. No problem. ठीक है.
So, Bibi sir, can you able to listen me?
Yes, sir.
Sir, when we are working with some open source EDA tools,
Yes.
they used to some minimum hours. Then afterwards, we have to go for some license and some sort of open source EDA is asking. Whether all the tools which you have mentioned here will have such things are okay, you can.
No, sir.
work
No.
fully.
Actually, whatever the tools I have shared, I'm using from 2020.
Okay.
So that's where it started. So that is a very basic tool, and it is almost 5 year completed. So all these 5 years, there are few systems with our students. It is running 24/7 for more than 3-4 months. We are designing multiple things. We'll keep on test it again and again as a research. So it is not like that. So may I know which tool you are using? Mohammed sir, I think you have muted.
Sir, actually, there's one tool. I could not get that name. Actually, it is EDA automations. When I
Okay,
take
you are
some
using it. Okay, you are using for IC design or electronic design or FPGA for which portion?
for IC designs, basic RTL design
Semi.
and verifications.
Okay, then it's semi-custom RTL. Then you can use the open lane. Yosis is the base for maximum of the open source tool. So open lane still they are providing in a better way. So you can go for it. That is completely free. You can use that too. You can run it with some low configuration system also. You don't need much high configuration.
Okay, sir. Thank you, sir.
I think we can conclude the session, sir.
Yeah. Thank you, ma'am, and thanks for patiently listening this much time. And sorry if I make you to sleep. I hope the session will give you at least some useful information about it.
Sir, thank you so much, sir, for accepting the invitation and delivering this session despite your busy schedule.
Yeah. Thank you.
Thank you, sir. Thank you. A very good evening, everyone. Congratulations on your successful submission of your test. I hope few of you got the certificates, and many of you who haven't received the certificates, there is no need to worry. Uh, when we submit the attendance, final attendance, and your marks to the portal, you will be getting your certificate. So there is no need to worry. Definitely, you will be getting your certificates. So that I can assure you. If you have any doubts, meanwhile you can post it in the group. We are always available to clarify your doubts. And now finally we have reached the valedictory session. We now reached the final segment of our FDP. So it is a moment to look back on what we achieved together, to acknowledge the efforts of many, and to close the program on a positive note. So to begin with, I invite Dr. R. Nagendra sir, coordinator of this FDP, to deliver the welcome address and walk us through the highlights of our FDP program. Sir, please.
Yeah, thank you, madam. And good evening, the dignitaries and my dear participants.
So the Department of Electronics and Communication Engineering, Sri Rama Engineering College, has successfully organized AICTE sponsored 1 week online faculty development program on intelligent VLSI design automation using AI techniques from 8th September 2025 to 13th September 2025. So this program aimed to enhance the knowledge base of faculty and researchers in integrating artificial intelligence and with VLSI design automation, thereby bridging the gap between processes of traditional VLSI design and emerging intelligent methodologies in VLSI. So the objectives of the program were to provide participants with a comprehensive understanding of VLSI domain automation frameworks, introduction to AI/ML application for solving optimization problem in VLSI design, exploring current research trends in AI-driven VLSI automation. So the program was spanned for 6 days, consisting of expert lectures with interactive discussions. So coming to the day-wise highlights, the FDP was started with inaugural session on day 1, that is on the 8/9/2025, followed by lecture 1 on design of VLSI architectures of post-quantum algorithms, delivered by Dr. P. Vikram Kumar, Associate Professor, Department of Electrical Engineering, IIT Tirupati. And on the same day, the lecture 2 was delivered by Dr. M. Sivasubramaniam Medasani, Senior Consultant, Cybiotics Technologies Private Limited, Kurnool. So he has delivered on the topic transistor to chip, exploring the role of MOSFETs in VLSI systems. Coming to the day 2, the first session was delivered by Dr. B. Naresh Kumar Reddy, Assistant Professor, Department of ECE, NIT Trichy, on the topic RISC-V-based system design with AI-enabled co-processors. The second session was delivered on designing high-speed and low-power ASICs using scalable memory compilers by Mr. P. Virendra Reddy, Senior Manager, IP Applications, Alpha Wave Semiconductor Private Limited, Bengaluru. And on day 3, the first topic was given by Dr. B. Chandrababu Naik, Assistant Professor from NIT Trichy. So he had delivered lecture on integrating VLSI with Industry 4.0, a new era of smart manufacturing. Later, the topic 2 was delivered by Mr. V.R. Pradeep Bharadwaja, Senior Manager, DFT Synopsys India Private Limited, Bengaluru. And on day 4, the talks were given by Dr. Ekta Goyal, Assistant Professor of ECE from NIT Warangal, and she delivered her lecture on nanoscale semiconductor devices, low power applications. So the second topic was on From Code to Silicon, AI powered revolution in RTL design workflows by Dr. Shanmuga Kumar Vargesan. He is the CEO of Matic Private Limited, Chennai. On day 5, the first session started with applications of artificial intelligence tools in VLSI design by Mr. Avinash Yerlapati, VLSI design engineer manager, Altera, Malaysia. The day was closed with the lecture on AI/ML for VLSI design by Dr. Sheikh Noor Muhammad, Associate Professor, Department of CSE, IIIT, Kanchipuram. Finally, on day 6, the first session started on low power VLSI design and edge computing, delivered by Mr. Nimit Gandhi, Staff Engineer, Lattice Semiconductors, Penang, Malaysia. The second session was on advanced FPGA technology reconfiguration, timing and accuracy acceleration, delivered by Mr. PVSR Bharadwaja, FPGA Design Engineer, Granite Labs Technologies Private Limited, Bengaluru. And the final topic was delivered by Dr. M. Dayalakumar, Founder and CEO, Mr. Gen Technologies Private Limited, Chennai, and he had delivered on the topic Open Source EDA with Integration. So the resource persons were delivered. There were 5 eminent academicians, 6 industry experts, and 2 overseas industry experts. So all the resource persons had given excellent and informative sessions on the topic. So there were 155 registrations in total from various states, universities, and industries, out of which more than 80% of the participants had actively attended the FTP on all the days. So the FDP on intelligent VLSI design automation using AI techniques successfully fulfilled its objectives by equipping participants with knowledge on state-of-the-art AI-driven VLSI automation methods. The program fostered academic enrichment, research motivation, and collaborative spirit among participants, making it as a significant academic achievement. I take this opportunity to thank the Honorable Chairman, Director, our Principal, Program Coordinator in particular, our faculty, senior faculty, staff, and students for extending their support in conducting this FDP successfully. And my heartfelt thanks to Dr. N. Vasu, Principal in Charge, Dr. M. Munishankar, HOD of EEE Department, Faculty of EC for extending their endless support in completing this event. I especially congratulate and thank the participants for attending all the sessions in this FDP and made it a grand success. Thank you. Thank you all.
Thank you, sir, for the detailed summary and for steering the program so effectively. Actually, the best measure of any program is the participants' voice. May I now invite a few participants to briefly share their feedback and experience.
Somebody please come forward to give oral feedback. It can be positive or negative. We need feedback to improve ourselves, please.
So good evening. This is Dr. M. Jagdishwari from Sri Ramakrishna Engineering College, Coimbatore. At the outset, I would like to congratulate Sri Rama College of Engineering for bringing in this FDP on intelligent VLSI design automation using AI techniques. Sir, am I audible?
Yes,
yes, madam. Please go on.
Yes, sir. Actually, as you said, the VLSI traditional techniques is what we have been familiar with of implementation and simulation and all that. So this AI implementation in VLSI technique, we had, the context which has been taken in this FDP is very much useful for us to go with AI techniques in VLSI. So this is one thing which we had learned from this FDP. And most of this, as you said, around 6 industry participants, along with major academicians and also overseas, resource persons, have given a very beautiful insight into how AI techniques have can be employed for VLSI applications. So this 6-day, really, we had a very good time, and really it will be useful for us, and we will take up the research on AI in VLSI design. Thank you so much, organizers of Sri Rama College of Engineering, for taking this recent topic and hot topic in VLSI and giving us a very good insight. Thank you so much for organizing. And as a participant, really, I have enjoyed all these 6 days. Thank you so much.
Thank you so much, madam. Others, please, we need your valuable feedback.
Sir, good evening.
Sir, good evening, sir.
Sir, this is Dr. Manihinda Babu, Associate Professor from Sri Ramakrishna Engineering College, Coimbatore. Sir, I sincerely thank the organizers for making this FDP good sessions. It was very interesting. And the choice of the topics, the resource persons, was very smoothly conducted, and it was a commitment that is made by the team for making this FDP a successful one. Each session was highly enriching, and it provided us insights and opportunities for academic growth. And I thank all the team members and the coordinator of this program for helping us by providing the Google Forms at the time when we face some issues in the ATAL web portal. I thank everyone for that. Thank you, sir. And I wish all success for future programs that you conduct in your organization. Thank you.
So thank you, both of you, for your wonderful feedback, sir and madam. Thank you.
Thank you, sir.
So others may please provide the feedback.
We really want to hear your feedback. We just want to know our lapses and how we want to improve ourselves in the future programs. Please help us.
Hello. Hello.
Sir, please go ahead.
Sir, good evening, sir. Thank you very much for sharing your valuable information, sir. I am from HVC Kadapa, sir. Thank you very
Okay,
much.
sir. Thank you, sir. Thank you so much, sir.
Good evening, everyone.
Yeah, good evening, madam. Please.
I, Dr. Sunita, Assistant Professor G. Narayanamma Institute of Technology, Hyderabad. Thanks to Sri Rama Engineering College for conducting such a wonderful FDP. And the sessions were highly informative and useful for enhancing knowledge in this emerging area, sir. Thank you so much.
Thank you so much, madam. So your feedback really means a lot for us. So we can we will get energy, and we can move forward in conducting many more sessions, many more programs like this. Thank you.
Good evening, sir. Nagendra, sir.
Yeah, sir. Good evening, sir. Sir, please.
I am Dr. Srihari, sir, head of the department, SVC Chittoor, sir.
Sir, tell me.
And, your effort made by the entire team is very good, sir. And the efforts made by the Shruti madam, yourself, and Shweta ma'am, and all those things, all the persons. The first thing is, the only one thing what I want to tell here is, at least we cannot able to find the gap between the session to session. At least 15-20 minutes gap, because one person has been continuously prolonged from beyond 7:30, 7:45, 8 up to 8. Without gap, until continuously it has been switched over to next session. Because of charging problems will be there, so many problems will be there once it is continuously conduct the FDPs. At least from next time onwards, at least 15 minutes gap. It means we can ask, we can request the other person to start within 10 minutes late, like that. At least we'll have some breathing time, because continuous today also from afternoon 2:30 onwards, continuously we are in online. Okay, that's the continuous means nearly 6 hours. Okay, that's the only thing. Everything is good and fine, sir. All the best for your future projects. Thank you.
Sir, thank you, sir. Actually, we also came to know the problem once the program had started on first day. From next time onwards, we definitely will have a half an hour break, sir. Thank you, sir. Thank you so much. Really, it is difficult to sit for those many hours. So definitely we will have some break in between sessions. Thank you, sir.
Good evening, sir. Can you able to listen to me?
Yes, sir. Please.
Okay, so this is Mohammed Mian from Abdullah Engineering College, Vellore district, Tamil Nadu. Thank you for providing such a very good FTPs are. Most of the topics, when I saw these topics and AI, and I was one of the person to ask more number of questions, if I'm correct, in this FDP.
Yes, sir, we noticed it.
Okay, sir. And it was going very well. And the timing, it's adult what they have given. This is the time you have to follow. The only thing is the speakers. Okay, this is the time we have to talk. This is the time you have to go for questions and all. Because we have organized this ATAL FDP. This was the one of the problem. And after all the good things, something has to get bad. That was happened today. And in the
Okay.
ATAL FDP, even when I was at that time when I was attending the test, there was no Google link, and even to submit one answer to go to the next answer, it was taking time. Okay, at least sometimes 1 minute or 2 minutes, maybe depends upon the network, or because uh, right now so many FDPs are going around the
Yes,
India.
sir.
So all will be using this ATAL websites, especially to give their feedbacks, to get in login. That is one of the major issues we have. So after so much time, many of them you can see many of the messages they have put in the WhatsApp group also. Even I have put one bigger message. You can see that is one of the main problems. So after coming out, even we could not log in. Then we have to go for this Google form. Then we have to enter.
Yes,
Hardly we
sir.
have to enter. I don't know how many answers I have entered correctly after leaving from ATAL. So other than that, it was a
Okay.
very good session. And sir, today's have yesterday's and today's presentations. If you are having, please share it in the WhatsApp group, sir.
Definitely we will share, sir. So actually we
Thank you,
got
sir.
busy in organizing, solving the issues. So we'll definitely, once everything is settled, we'll send you the, and please be on what you call it, this WhatsApp group, sir. So we will be
Yes.
posting there videos.
Okay, sir. Thank you, sir. And thank you,
Okay.
Shruti madam, for answering all our queries, madam.
Thank you, sir. Thank you.
So now it's time to go for vote of thanks, and before that, if anybody wants to give feedback, you can give. Shruti madam, I think it's time to go for closing the session, madam. Please.
Sir, yes, sir. So thank you everyone for your honest reflections and suggestions. Now it is the time for vote of thanks. First and foremost, I express a deep gratitude to AICTE Atal Academy for entrusting us with this FDP and for the continuous encouragement in fostering faculty development. Our heartfelt thanks to all the distinguished resource persons who have enriched us with their expertise, knowledge, and thought-provoking sessions over the past 5 days. I also extend my sincere thanks to our management, respected principal, whose cooperation and motivation kept us moving forward smoothly. We are profoundly grateful to our Vice Principal, Dr. N. Vasu sir, whose constant encouragement and support have been instrumental in the successful conduction of this program. We are deeply grateful to Dr. Munishankar sir, Head of the Department of EEE, and Mr. T. Koshaleshwar Reddy, our IQAC coordinator, for their continuous guidance and keen involvement in the success of this FDP. A very special note of thanks to Dr. Prabhakar Reddy sir for his invaluable guidance and unwavering support in this FDP. A word of appreciation is due to our participants who have joined with enthusiasm, actively interacted, and made this FDP meaningful and engaging. Last but not least, I would like to thank the organizing and technical teams working behind the scenes and all the faculty of Sri Rama Engineering College who ensured that every session was conducted seamlessly. With with gratitude to everyone who contributed to the success of this FDP, we now bring the program to a close. May the learnings we gained here translate into impactful teaching, innovative research, and professional growth. Let's sign off today, not with an ending, but with a promise to apply, share, and multiply the knowledge we have gained here. Thank you all once again.
I
A small
request
request,
yeah,
a
please go
small
ahead, madam.
request from my side. If you people don't mind, I want to make this event memorable. Can you please switch on the camera so that we have snapshots of this event?
So dear participants, can you please switch on your videos, cameras, so that we will take a snapshot. Madam, have you taken a snapshot?
Thank
Okay, thank you, sir. Thank you so much.
Thank you, sir.
Yeah, thank you, sir. So you may please now leave the meeting, sir. Thank you all. Good night. Have a great day.